A star 40 times more massive than our Sun is about to die. Not in a few billion years, not in a few centuries, in the next few seconds. And what happens next is not a supernova. It is something far more violent, something that will briefly outshine every star in its host galaxy combined. Something that will punch a hole in the fabric of space-time itself and leave behind an object that was never supposed to exist. Right now, deep in its core, an iron heart is collapsing, not slowly, not gracefully, faster than the speed of sound, faster than light can cross the dying star's interior. In less than 1 millisecond, thousands of kilometers of stellar mass will compress into a region smaller than a city. The core will fall past every threshold physics recognizes, past atoms, past neutrons, past the point where matter has any meaning at all. And then it will vanish behind an event horizon, sealing itself off from the universe forever. But before it disappears, it will scream. 2 jets of plasma will erupt from the poles of the newborn black hole, accelerating to 99% the speed of light. They will drill through the star's outer layers like bullets through paper. And when they break free into open space, they will unleash a gamma-ray burst, so luminous, so concentrated, that for 10 seconds it will release more energy than our Sun will produce in its entire 10 billion-year lifetime. This is a hypernova, the most violent death in the modern universe. A cataclysm so extreme it defies every intuition you have about how stars are supposed to end. And yet, it is not just destruction. Because in that collapse, in that inferno of radiation and shattered nuclei, the heaviest elements in existence are forged and flung across the cosmos. The gold in your ring, the uranium in reactor cores, the building blocks of worlds yet to be born. This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Chapter 1. There are stars in the universe that live fast, burn bright, and die screaming. Not metaphorically, literally. Their deaths are so violent, so energetic, that they send shockwaves across billions of light years. And at the center of that story is a star weighing 40 times the mass of our Sun. Not just any star, a titan, a cosmic monster whose entire existence is a countdown to annihilation. To understand what happens at the end, you first have to understand what this thing is, because a 40 solar mass star is not just a bigger version of the Sun. It is a fundamentally different kind of object, playing by fundamentally different rules. And everything about its life, from the moment it ignites to the second it collapses, is a lesson in how the universe builds scale and then tears it apart. Stars are born in nurseries, enormous clouds of gas and dust called giant molecular clouds, sprawling structures that can weigh anywhere from 1,000 to 10 million times the mass of the Sun and stretch across hundreds of light years. These clouds are cold, dark, and quiet most of the time. But somewhere inside that quiet, gravity is always working. It pulls, it tugs. It gathers matter into denser and denser pockets until something tips. When a region inside one of those clouds gets dense enough, it collapses, not slowly, fast. The gas rushes inward, dragging more material with it, heating up as it compresses. At the center of that collapse, a core forms. A protostar. If the conditions are right, if there is enough mass and enough pressure, that core will keep collapsing until the temperature at its center hits 10 million Kelvin. That is the ignition point. That is where hydrogen fusion begins. Hydrogen fusion is the fire that powers every star. 4 hydrogen nuclei slam together under immense pressure and heat, fusing into a single helium nucleus. The process releases energy, a lot of energy, enough to counterbalance the crushing weight of the star's own gravity. That balance, that tug of war between inward collapse and outward radiation pressure, is what keeps a star stable. It is what defines a star's life on what astronomers call the main sequence, the long middle chapter where most stars spend most of their existence just sitting there, burning hydrogen, holding steady. Our Sun has been doing that for about 4.5 billion years. It will keep doing it for another 5 billion. The smallest stars, the cold red dwarfs, can stay on the main sequence for hundreds of billions of years. The universe is not even old enough yet for a single one of those stars to have died of old age. They are misers. They burn their fuel so slowly that they will outlast galaxies. A 40 solar mass star does not have that luxury. It is not a miser, it is a furnace. To hold up 40 times the mass of the Sun, you need 40 times the pressure. More than 40 times, actually, because gravity does not scale linearly. The core of a 40 solar mass star has to burn hotter, brighter, faster. The hydrogen fusion happening at its center is not a slow smolder, it is a roar. And because it is burning so fast, it runs out of fuel fast. A 40 solar mass star stays on the main sequence for only a few million years. That is it. A few million years to do what the Sun will do over 10 billion. If you compressed the Sun's entire main sequence life into a single human lifespan of 80 years, a 40 solar mass star would live for about 2 months. Born, burned out, gone. That short lifespan is not a defect, it is a feature. Massive stars are the sprinters of the cosmos. They live hard, they die young, and in the process they forge the heavy elements that make planets and people possible. But we are getting ahead of ourselves. First, we have to understand what it means to be 40 solar masses in the first place. 1 solar mass is the mass of our Sun. Roughly 2 times 10 to the power of 30 kilograms. That is a 2 followed by 30 zeros. It is an incomprehensibly large number. The Sun contains 99.86% of all the mass in the entire solar system. Everything else, all the planets, all the moons, all the asteroids, all the comets, all the dust, all of it combined adds up to less than 0.2%. Jupiter, the largest planet, is a rounding error compared to the Sun, and a 40 solar mass star is 40 of those. Scale matters. When you pack that much mass into a single object, the core pressure becomes so extreme that the physics starts to shift. The temperatures climb so high that fusion does not just happen, it dominates. The luminosity, the total energy output of the star, scales with mass in a way that is almost obscene. A star twice the mass of the Sun is not twice as bright, it is roughly 10 times brighter. A star 40 times the mass of the Sun can be hundreds of thousands of times more luminous. Some estimates put it even higher. If you could somehow replace the Sun with a 40 solar mass star, Earth would not just get warmer, it would vaporize instantly. The heat output would be so intense that the oceans would boil away in seconds. The atmosphere would be stripped off, the rocky surface would melt, and that is from 93 million miles away. Imagine standing on the surface of that star. You could not, of course. There is no surface, just layers of gas, so hot and so dense that they blur the line between solid, liquid, and plasma. But if you could somehow hover at the photosphere, the visible outer layer, you would be staring into a cauldron of nuclear fire, pumping out more energy in a single second than human civilization has used in its entire history. And yet, the star holds. Gravity pulls inward with the weight of 40 suns. Radiation pressure pushes outward with the force of hundreds of thousands of suns worth of luminosity. The two forces balance, barely. The star does not collapse. It does not explode. It just sits there, fusing hydrogen into helium, holding the line. The core is where it happens. At the very center of the star, where the temperature exceeds 15 million Kelvin, hydrogen nuclei move fast enough to overcome their mutual electromagnetic repulsion and slam together. The proton-proton chain reaction, the same process that powers the sun, kicks in. 4 protons become one helium nucleus. The mass of that helium nucleus is slightly less than the combined mass of the 4 protons that made it. The missing mass, about 0.7%, gets converted into energy according to Einstein's equation, mass times the speed of light squared. That tiny bit of missing mass turns into a flood of gamma-ray photons and neutrinos. The gamma rays scatter through the dense core, slowly working their way outward over thousands of years, while the neutrinos, which barely interact with matter at all, shoot straight out into space at the speed of light. By the time the light from the core reaches the surface, the photons have been absorbed and re-emitted so many times that they have lost most of their energy. They arrive at the photosphere as visible light and infrared radiation pouring out into the void. The star glows. Not because it is hot, though it is, but because it is fighting. Every photon leaving the surface is a small victory against gravity. Every second the core keeps fusing hydrogen is another second the star does not collapse. And for a 40 solar mass star, every second is expensive. The fusion rate at the core is so high that the hydrogen supply, vast as it is, burns away at a ferocious pace. While the sun will fuse hydrogen for 10 billion years, this star will exhaust its core hydrogen in just a few million. There is no way around it. The bigger the star, the shorter the life. That rule holds across the entire mass spectrum. Red dwarfs, the smallest true stars, can weigh as little as 0.075 solar masses. They fuse hydrogen so slowly that their main sequence lifetimes stretch into the trillions of years. Yellow dwarfs, like the sun, sit in the middle, 10 billion years, give or take. And then you get to the top end, the massive stars. 8 solar masses and up. Their lives are measured in millions of years, sometimes tens of millions if they are on the lighter end of massive, but rarely more than that. And the truly gigantic ones, the stars pushing 100 solar masses or more, might only live for 1 million years, maybe 2. The reason for this inverse relationship between mass and lifespan is simple. The more mass you have, the hotter your core has to be to support that mass. The hotter your core, the faster you fuse hydrogen. The faster you fuse hydrogen, the sooner you run out. A massive star is not just burning brighter, it is burning faster. And once the hydrogen is gone, the clock really starts ticking. We know how many stars exist in the universe, roughly. The estimates vary, but the current best guess puts the total number somewhere around 1 septillion. That is a 1 followed by 24 zeros. Most of those stars are small. Red dwarfs make up about 70 to 80% of all stars. The sun-like yellow dwarfs are rarer, maybe 10% of the total. And the massive stars, the ones we are talking about here, the ones that weigh 8 solar masses or more, make up less than 1% of the stellar population. But that 1% does all the heavy lifting, literally. Massive stars are the forges of the cosmos. They are the only stars capable of fusing elements heavier than helium in significant quantities. They are the ones that produce carbon, oxygen, nitrogen, silicon, sulfur, and eventually iron. They are the ones that explode as supernovae, scattering those heavy elements into space where they seed the next generation of stars and planets. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was made inside a massive star. And then that star died and threw its guts across the galaxy so that billions of years later those atoms could end up in you. Our own Milky Way galaxy contains more than 100 billion stars. Most of them are small. Most of them will never explode. Most of them will just fade away quietly, cooling into white dwarfs over timescales longer than the current age of the universe. But scattered among those 100 billion are the giants, the massive stars, the ones that matter, and one of them, somewhere out there, right now, is a 40 solar mass star sitting on the main sequence, burning hydrogen, completely unaware that it has only a few million years left. It is worth pausing to appreciate what that star is doing right now. At this very moment, deep in its core, billions upon billions of fusion reactions are happening every second. Protons are colliding, helium is forming, energy is flooding outward. The radiation pressure from all that fusion is holding up 40 times the mass of the Sun. The temperature at the core is higher than anything we can produce on Earth. The density is so extreme that a teaspoon of core material would weigh several tons, and the whole thing is stable. For now, that stability will not last. It cannot, because hydrogen is finite, and once the core runs out, the rules change, the balance tips, and the star begins the next phase of its life. A phase that will take it through a gauntlet of fusion stages, each one hotter and faster than the last, each one burning through its fuel supply in a fraction of the time the previous stage took. Hydrogen lasts millions of years, helium lasts hundreds of thousands, carbon lasts centuries, silicon lasts days, and then there is nothing left to burn, and the star dies. But that death is not quiet, it is not gradual. It is not a slow fade into darkness. For a 40 solar mass star, death is an explosion, a catastrophic collapse followed by a rebound so violent that it tears the star apart and sends jets of matter screaming outward at 99% the speed of light. The explosion releases more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. And at the center of that explosion, where the core used to be, a black hole is born. That is where this story is headed. But to get there, we have to follow the star through every stage of its life. We have to watch as it exhausts its hydrogen, contracts, heats up, and ignites helium. We have to see it build heavier and heavier elements in its core, layer by layer, like an onion made of fire. We have to understand why fusion stops at iron and what happens when it does. And we have to watch the final seconds as the core collapses, rebounds, and explodes, because every step of that process is written into the physics of the star from the moment it first ignited. The ending was inevitable. The star just did not know it yet. The hydrogen is gone. That is the first turning point. After a few million years of steady fusion, converting hydrogen into helium at a rate that would make the Sun look lazy, the core of our 40 solar mass star has exhausted its primary fuel. Not all the hydrogen in the star. Just the hydrogen at the very center, where the temperatures and pressures are high enough for fusion to occur. The outer layers are still loaded with hydrogen, but that hydrogen is too cool, too diffuse, too far from the crushing weight of the core to ignite. It just sits there, waiting. When the core runs out of hydrogen, the fusion stops. No more energy flooding outward. No more radiation pressure holding up the star. And gravity, which has been waiting patiently for this moment, starts to win. The core contracts. Not slowly, fast. As it contracts, it heats up. That is basic thermodynamics. Compress a gas and its temperature rises. The same principle that makes a bicycle pump warm to the touch after you use it. Except this is not a bicycle pump. This is the core of a star weighing 40 times the mass of the Sun, and when it compresses, the temperature does not rise by a few degrees, it rises by millions. The contraction heats the core until the temperature climbs past 100 million Kelvin. At that point, something new happens. Helium fusion ignites. Not the same helium fusion that happens in low-mass stars like the Sun, which goes through a brief unstable phase called the helium flash. In a massive star, helium fusion begins smoothly, almost gently, because the core is already so hot and so dense that the transition is seamless. 3 helium nuclei, each containing 2 protons and 2 neutrons, slam together in a process called the triple alpha reaction. The result is a single carbon nucleus. Sometimes a 4th helium nucleus joins the party, and you get oxygen instead. Either way, the core is now fusing helium into carbon and oxygen, and the energy output from that fusion is enough to hold the star up again. The balance is restored, for now. But here is the thing. Helium fusion does not last as long as hydrogen fusion, not even close. A 40 solar mass star burns hydrogen for a few million years. It burns helium for maybe a million years, maybe less. The reason is simple. Helium fusion releases less energy per reaction than hydrogen fusion. To produce the same amount of outward pressure, the star has to fuse helium faster, and faster means the fuel runs out sooner. It is a losing game from the start. While the core is busy fusing helium, the hydrogen that was left behind in the outer layers finally gets its moment. The heat from the contracting core pushes outward, raising the temperature in a shell of gas surrounding the core. That shell, which still contains hydrogen, gets hot enough to ignite. So now the star is fusing hydrogen in a shell around a core that is fusing helium. 2 fusion zones stacked on top of each other. Astronomers call this shell burning, and it changes the star's appearance dramatically. The outer layers of the star, heated by the energy pouring out from both fusion zones, expand outward. The star swells. Its surface cools as the outer layers spread out, and the color shifts from blue-white to red. The star has become a red supergiant. If you could see this 40 solar mass star from a distance, you would notice the change immediately. What was once a compact, blazing hot blue star is now an enormous, bloated red giant. The surface temperature has dropped to maybe 4,000 Kelvin, cool by stellar standards, but the size has increased so much that the total luminosity, the total energy output, has actually gone up. The star is now hundreds of thousands of times brighter than the Sun. Some red supergiants get so large that if you placed them at the center of our solar system, their outer layers would reach past the orbit of Mars, maybe even Jupiter. And the whole thing is still held together by gravity, barely. Inside the core, helium keeps fusing into carbon and oxygen. Layer by layer, the core builds up heavier elements, and then, inevitably, the helium runs out too. Same story. Fusion stops. The core contracts, the temperature rises, and at around 600 million Kelvin, carbon ignites. Carbon fusion is a different beast entirely. The temperatures and pressures required are so extreme that the reactions happen in sudden, violent bursts, rather than the steady burn of hydrogen or helium. 2 carbon nuclei slam together and produce a whole range of possible products: neon, sodium, magnesium, sometimes just helium and oxygen. It depends on the energy of the collision and the angle. The result is a messy, chaotic fusion environment that produces a mix of elements rather than a single clean output. Carbon burning lasts about 1,000 years, not 1,000 centuries, 1,000 years. The star has gone from millions of years on hydrogen to a millennium on carbon. The clock is speeding up. And with each new stage, it speeds up more. By now, the star has developed a layered structure that astronomers call the onion skin model. Picture an onion, thin layers wrapped around each other, each one chemically distinct from the one below it. At the very center, you have the carbon and oxygen core, where carbon fusion is happening. Surrounding that is a shell where helium is still fusing. Surrounding that is a shell where hydrogen is fusing. And outside all of that, you have the enormous envelope of the star, filled with unfused hydrogen and helium that will never get hot enough to burn. Each layer is a record of the star's history. Each one represents a stage of fusion that has already ended at the core and moved outward into a shell, and each one is thinner and hotter than the one above it. The deeper you go, the more extreme the conditions, the higher the temperature, the greater the density, the shorter the timescales. It is a countdown, and the star is accelerating toward the finish line, whether it wants to or not. When carbon runs out, the core contracts again. Temperature climbs past 1 billion Kelvin, neon ignites. Neon fusion is even faster, even more violent. The neon nuclei break apart under the intense heat, producing oxygen and helium. Those products then fuse with other neon nuclei to make magnesium. The whole process takes about 1 year. 1 year. The star has gone from millions of years on hydrogen to a single year on neon. The collapse is no longer slow. It is approaching freefall in terms of evolutionary timescales. A star that once had millions of years to figure itself out now has months. Then oxygen. Oxygen fusion ignites at around 2 billion Kelvin. 2 oxygen nuclei collide and produce silicon, sulfur, phosphorus, and a handful of other mid-weight elements. Oxygen burning lasts about 6 months. 6 months to exhaust the entire oxygen supply at the core. By now, the onion has more layers than you can easily count. A silicon-rich core, surrounded by a shell burning oxygen, surrounded by a shell burning neon, surrounded by a shell burning carbon, surrounded by shells burning helium and hydrogen. Each layer is a furnace. Each one is pouring energy outward, trying desperately to hold up the weight of the layers above it, and each one is living on borrowed time. Finally, silicon. Silicon fusion is the last stage. It ignites at temperatures exceeding 3 billion Kelvin. The core is now so hot, so dense, that the silicon nuclei do not just fuse into heavier elements. They break apart and reassemble in a cascade of reactions that builds up the periodic table, one nucleus at a time. Silicon becomes sulfur. Sulfur becomes argon. Argon becomes calcium. Calcium becomes titanium. The chain continues, step by step, element by element, climbing higher and higher in atomic number. And at the end of that chain, you get iron. Iron 56 to be specific, the most stable nucleus in the universe. Silicon burning lasts about 1 day, not 1 year, 1 day. In 24 hours, the core of a 40 solar mass star converts its entire silicon supply into iron, and then it stops. Because iron is where the rules change. Iron is where fusion stops being profitable. Every fusion reaction up to this point, from hydrogen to helium to carbon to oxygen to silicon, released energy. That energy kept the star alive. It provided the outward pressure needed to fight gravity. But fusing iron into anything heavier does not release energy. It consumes energy. Iron is the breaking point, the line in the sand. The end of the road. You can think of fusion as a process of moving towards stability. Lighter elements, when fused, release energy because the products are more stable than the reactants. The binding energy per nucleon, the amount of energy holding each particle in the nucleus together, increases as you move from hydrogen up to iron. That increasing stability is what powers stars. But past iron, the trend reverses. Heavier elements are less stable than iron. Fusing iron into something heavier would require you to put energy into the reaction rather than getting energy out. And a star, which has spent its entire life extracting energy from fusion, cannot afford to do that. The moment iron appears at the core, the game is over. The iron core grows, not through fusion exactly, but through the continued burning of silicon in the shell surrounding it. That silicon burns into more iron, and the iron piles up at the center, layer by layer, building a core that weighs more and more with each passing second. And the whole time, the core is trying to hold itself up with electron degeneracy pressure, not fusion. Fusion has stopped. Electron degeneracy pressure is a quantum mechanical effect that occurs when electrons are packed so tightly together that they resist further compression, simply because the laws of quantum mechanics forbid two electrons from occupying the same state. It is the same force that holds up white dwarfs, the remnants of low-mass stars like the Sun. And for a while, it can hold up the iron core of a massive star. But only for a while. There is a limit to how much mass electron degeneracy pressure can support. That limit is called the Chandrasekhar limit, named after the Indian astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s. The number is 1.4 solar masses. If the core weighs less than 1.4 times the mass of the Sun, electron degeneracy pressure can hold it up indefinitely. If the core weighs more than that, the pressure fails, the electrons get crushed, and the core collapses. A 40 solar mass star, by the time it finishes silicon burning, has an iron core weighing somewhere around 1.5 to 2 solar masses, comfortably above the Chandrasekhar limit. The core is doomed. It just does not know it yet. The whole journey from hydrogen to iron happens faster than the star's original main sequence lifetime. Hydrogen burning took a few million years. All the stages after that, helium through silicon, added up to maybe another million years. Total lifetime, maybe 5 or 6 million years. Compare that to the Sun, which will spend 10 billion years on the main sequence alone. A 40 solar mass star lives its entire life and dies before the Sun has even finished a tenth of its hydrogen supply. It is the difference between a mayfly and a human. One lives for a day, the other lives for decades. But on cosmic timescales, even the long-lived stars are mayflies, and the massive ones are over before they begin. Each stage of burning is hotter than the last. Hydrogen burns at 15 million Kelvin, helium at 100 million, carbon at 600 million, neon at 1.2 billion, oxygen at 2 billion, silicon at 3 billion. The temperatures climb exponentially, the timescales shrink exponentially. The star is not just running out of fuel, it is running out of time, and there is no way to stop it, no way to slow it down. The laws of thermodynamics are written into the structure of the universe, and they do not make exceptions. A star can only fuse elements up to iron. Past that, the physics says no. And when the physics says no, the star dies. There is something almost tragic about it. The star has been fighting gravity for millions of years. Every second of its life has been a battle between collapse and expansion, between the inward pull of its own mass and the outward push of fusion energy. And for millions of years, fusion won. The star held steady, it burned bright. It lit up the space around it. ionizing gas clouds, triggering the formation of new stars, shaping the structure of the galaxy it lived in. And now, after all that, the fuel is gone. The iron core sits at the center like a ticking bomb, and there is nothing the star can do to stop what comes next. The outer layers do not know yet. They are still burning. Hydrogen in the outermost shell, helium just inside that. Carbon, neon, oxygen, silicon, each layer stacked on top of the one below it, each one fusing away, pouring energy outward. The star still looks normal from the outside. It still glows. It still holds its shape. But at the core, where the iron has piled up past the Chandrasekhar limit, the collapse has already started. Not quickly, not yet, but the first cracks are forming. The electrons are starting to fail. The pressure is dropping. And in a few seconds, maybe a few minutes at most, the entire core is going to implode. The rebound from that implosion will tear the star apart in the most violent explosion the universe has to offer. And at the center, where the core used to be, a black hole will be born. That is the next part of the story. But before we get there, before we watch the core collapse and the jets erupt and the gamma rays scream across half the universe, we need to understand why iron is special, why it is the breaking point, why it is the element that kills stars. Because everything that happens next, everything that makes this the most violent death in the universe, starts with a single atom of iron sitting at the center of a star that has run out of moves. Iron does not care about your star's ambitions. Iron does not care that your star has spent millions of years building itself up from hydrogen, climbing the periodic table element by element, fusion stage after fusion stage, getting hotter and denser and more desperate with each new layer. Iron does not care that the star has fought gravity for its entire life and won every single round until now. Iron is the finish line, the brick wall, the place where the rules of nuclear fusion look at the star and say, "We are done here." For millions of years, fusion has been the star's lifeline. Every element it burned released energy. Hydrogen into helium, energy out. Helium into carbon and oxygen, energy out. Carbon into neon and magnesium, energy out. Neon into oxygen, energy out. Oxygen into silicon, energy out. Silicon into iron, energy out. Each stage gave the star something to work with. Each one produced enough outward radiation pressure to hold up the crushing weight of the layers above. The star was always walking a tightrope, balancing collapse against expansion, but as long as fusion kept running, the star had a chance. Iron ends that. Iron 56 is the most stable nucleus in the universe, not the heaviest, not the most common, the most stable. Stability, in nuclear terms, is measured by something called binding energy per nucleon. Every atomic nucleus is held together by the strong nuclear force, which glues protons and neutrons together, despite the electromagnetic repulsion trying to push the protons apart. The binding energy is the amount of energy you would need to rip that nucleus apart into individual protons and neutrons. Divide that energy by the number of particles in the nucleus, and you get the binding energy per nucleon. The higher that number, the more tightly bound the nucleus is. The more stable it is, the harder it is to break. Iron 56 sits at the top of that curve. It has the highest binding energy per nucleon of any element, 8.8 million electron volts per nucleon. That means if you want to fuse iron into something heavier, you have to put energy into the reaction. You have to push the nuclei together so hard that you overcome the fact that the product is less stable than the starting material. And that costs energy. It does not release energy, it consumes it. Fusion past iron is endothermic. Every reaction that builds elements heavier than iron is a net energy loss, and a star cannot afford energy loss. A star needs energy output. That is the entire business model. Fuse light elements, get energy, use that energy to hold yourself up. The moment fusion stops giving you energy, the moment it starts taking energy away, the star is out of moves. The iron core grows anyway. Not because iron itself is fusing into anything heavier. It is not. The iron just sits there, inert, piling up at the center of the star, like ash at the bottom of a furnace. The growth comes from the silicon burning in the shell just outside the core. That silicon is still fusing, still climbing the periodic table, producing sulfur and argon and calcium and titanium and eventually more iron. Every second, more iron nuclei rain down onto the core. The core gets heavier and heavier and heavier, and the whole time it is doing absolutely nothing to support itself. No fusion, no energy output, just mass, dead weight. A ball of iron sitting at the center of a dying star, waiting for gravity to notice. Gravity notices. By the time silicon burning finishes, the iron core weighs somewhere between 1.3 and 2 solar masses. That is a lot of iron. 2 solar masses is 4 times 10 to the 30th kilograms. Picture the sun. Now picture another sun. Now compress both of them down into a sphere a few thousand kilometers across and convert every atom into iron. That is what we are dealing with. And it is sitting there, holding itself up with nothing but electron degeneracy pressure. Electron degeneracy pressure is a quantum mechanical effect. When you pack electrons tightly enough together, they start to resist further compression, not because of heat or radiation, but because the Pauli exclusion principle forbids 2 electrons from occupying the same quantum state. Electrons are fermions. Fermions follow rules. One of those rules is that you cannot stack 2 identical fermions on top of each other. When you try to compress a gas of electrons, they push back, not with thermal energy, with quantum resistance. It is the same force that holds up white dwarfs. And for a while, it can hold up the iron core of a massive star. But there is a limit. Subramanian Chandrasekhar calculated that limit in the 1930s. He showed that electron degeneracy pressure can only support a maximum mass of about 1.4 times the mass of the Sun. The exact number depends on the composition of the core and how fast the electrons are moving, but the general principle holds. If your core weighs less than the Chandrasekhar limit, degeneracy pressure will hold it up indefinitely. If your core weighs more than the limit, the pressure fails. The electrons get squeezed so tightly together that they start moving at relativistic speeds, close to the speed of light. And electrons cannot move faster than light. That is a hard limit. Once they hit that speed, degeneracy pressure maxes out. It cannot increase any further. And if the gravitational force pulling inward is stronger than the maximum pressure pushing outward, the core collapses. A 40 solar mass star has an iron core weighing between 1.5 and 2 solar masses, comfortably over the limit. The core is doomed from the moment it forms, and it does not take long for the collapse to start. Within seconds of the last silicon fusion reaction, the core begins to fall inward, not slowly, not gradually, instantly. The collapse happens so fast that the word collapse barely captures it. Freefall might be more accurate. Implosion, catastrophic structural failure. The core, which was thousands of kilometers across, contracts to a few kilometers in under a second. Some estimates put the time scale at less than a millisecond, a thousandth of a second. Blink and you would miss it. Except you could not blink, because if you were anywhere near this event, you would be vaporized before your brain could process what was happening. The density climbs fast. At the start of the collapse, the core density is around 1 billion grams per cubic centimeter. That is already absurdly dense. A sugar cube of that material would weigh 1,000 tons, but that is just the starting point. As the core collapses, the density doubles, then doubles again, then again. Within a fraction of a second, the core density reaches 100 billion grams per cubic centimeter, then 400 billion, then 200 trillion. The numbers stop making sense in any human context. You are no longer talking about matter as we understand it. You are talking about atomic nuclei crushed together so tightly that the space between them disappears. You are talking about the protons and neutrons in those nuclei beginning to touch. You are approaching nuclear density. The density inside an atomic nucleus, 2.4 times 10 to the 14th grams per cubic centimeter. That is the density of a neutron star, and the collapsing core is heading there at a significant fraction of the speed of light. The temperature climbs too. When you compress a gas, it heats up. Basic thermodynamics. But this is not a gentle compression. This is the entire core of a star collapsing under its own weight at velocities measured in tens of thousands of kilometers per second. The temperature at the core, which was already sitting at around 3 billion Kelvin at the end of silicon burning, spikes to 10 billion Kelvin, then higher. The thermal energy becomes so extreme that something called photodisintegration kicks in. Photodisintegration is exactly what it sounds like. High-energy gamma-ray photons, produced by the insane temperatures, start slamming into iron nuclei and ripping them apart. Iron breaks down into helium. Helium breaks down into protons and neutrons. The process consumes energy, a lot of energy, about 2 million electron volts per nucleon. And that energy has to come from somewhere. It comes from the core. The photodisintegration saps heat from the collapsing core, which lowers the temperature, which lowers the pressure, which makes the collapse faster. It is a runaway process. The hotter the core gets, the more photodisintegration happens. The more photodisintegration happens, the more energy gets pulled out of the core. The more energy gets pulled out, the faster the collapse. There is no braking mechanism, no way to slow it down. The core is in free fall and picking up speed, and then the electrons start to disappear. At densities above 10 billion grams per cubic centimeter, something else happens. Protons and electrons, which have been sitting next to each other as separate particles for the entire life of the star, start to merge. The process is called electron capture. A proton absorbs an electron and becomes a neutron. The reaction also produces a neutrino, a tiny, nearly massless particle that interacts so weakly with matter that it can pass through the entire Earth without hitting a single atom. Under normal conditions, electron capture is rare, but these are not normal conditions. The density is so high that protons and electrons are being crushed into each other with so much force that the reaction becomes common, then frequent, then constant. The electrons, which were providing the degeneracy pressure holding up the core, are vanishing, being converted into neutrons and neutrinos. The pressure drops and the collapse accelerates. The neutrinos flood out. Neutrinos do not care about matter. They do not interact with it. At normal densities, a neutrino could pass through a light year of solid lead without hitting anything. But the core of a collapsing star is not normal density. It is so dense that even neutrinos start to get trapped. At densities above 1 trillion grams per cubic centimeter, the neutrinos cannot escape fast enough. They scatter off the nuclei. They scatter off each other. They deposit energy into the core. For a brief moment, neutrino pressure actually adds to the total pressure trying to hold the core up. But it is not enough, not nearly enough. The gravitational force pulling inward is so strong that even the neutrinos, with all their energy, cannot stop it. They slow the collapse slightly. That is all. The core keeps falling. The outer layers of the core do not know what is happening yet. Light travels fast, 300,000 kilometers per second, but even at that speed, it takes time for information to propagate outward. The innermost part of the core collapses first. The layers just outside that are still falling inward, but they have not hit the center yet. The layers outside those are still contracting, but they have not started the freefall phase. And the layers outside those, the shells where oxygen and neon and carbon are still burning, are still fusing away, completely unaware that the core beneath them has disappeared. The star, from the outside, still looks normal. It is still glowing. It is still radiating energy. It is still a star. But at the center, in the space where the core used to be, the laws of physics are rewriting the rulebook in real time. Here is the thing about iron that makes this collapse inevitable. Every element lighter than iron, when you fuse it, releases energy because the product is more stable than the starting material. You are moving up the binding energy curve, closer to iron, closer to stability. Fusion is exothermic. It heats the core. It produces radiation pressure. It holds the star up. But once you have iron, you are at the top of the curve. There is nowhere to go. Fusing iron into anything heavier moves you down the curve, away from stability. The products are less tightly bound than iron, less stable. And that means the reaction costs energy instead of producing it. The core cools instead of heating. The pressure drops instead of rising. And without pressure, gravity wins. Instantly, completely, irreversibly. You could think of the iron core as a white dwarf that formed inside a star instead of after the star died. White dwarfs are the remnants of low-mass stars like the Sun. When the Sun runs out of fuel, it will shed its outer layers and leave behind a core made of carbon and oxygen about the size of the Earth, held up by electron degeneracy pressure. That core will sit there for trillions of years, cooling slowly, never collapsing, because it weighs less than the Chandrasekhar limit. A 40 solar mass star does not get that option. Its core is already over the limit by the time it forms. It is an unstable white dwarf, a white dwarf that has no business existing, and the universe corrects that mistake in less than a second. The collapse is not just fast, it is faster than anything else happening in the star. Faster than the fusion reactions in the outer shells, faster than the sound speed in the surrounding gas, faster than the light travel time across the core. The innermost region of the core, about 7/10 of a solar mass, collapses and rebounds before the outer layers even realize what is happening. That rebound is what turns the collapse into an explosion. When the inner core hits nuclear density, it suddenly stiffens. The neutrons, packed together as tightly as the laws of physics allow, resist further compression with a force so strong that the core bounces, not elastically, not gently, violently. The rebound sends a shock wave racing outward at 70,000 kilometers per second. That is about a quarter of the speed of light. And when that shock wave hits the infalling outer layers of the core, which are still collapsing inward at similar speeds, the collision releases more energy than the Sun will produce in its entire 10 billion year lifetime. The explosion has begun, but we are not there yet. First, the core has to finish collapsing, and what forms at the center is not a neutron star, not for a 40 solar mass star. The core is too heavy, the mass is too high. Neutron degeneracy pressure, the force that holds up neutron stars, has a limit too, and a collapsing core weighing 1.5 to 2 solar masses is right at that limit, maybe over it. If the core weighs more than about 2.2 solar masses, not even neutron pressure can stop the collapse. The core does not bounce, it does not form a neutron star. It keeps collapsing, past nuclear density, past any density that has a name. The core collapses into a singularity, a point of infinite density where the laws of physics as we understand them stop working. The core becomes a black hole. And the rebound, if it happens at all, happens around the black hole rather than inside it. The shock wave still forms, the explosion still happens, but at the center, where the core used to be, there is now a region of space-time so warped that not even light can escape. A newborn black hole weighing about 2 solar masses, sitting at the heart of a star that is about to tear itself apart. That process, from the first moment of collapse to the formation of the black hole, takes less than a second. The star has gone from a stable, fusing, luminous object to a collapsing core on the edge of oblivion in less time than it takes you to read this sentence. And the collapse is not slowing down, it is accelerating. The iron core, which took millions of years to build, is gone, obliterated. Compressed into a black hole in the time it takes light to travel from the Earth to the Moon. And the energy released by that collapse, carried outward by neutrinos and shock waves, and eventually by jets of matter moving at 99% the speed of light, is about to announce to the rest of the universe that something has died, not quietly, not peacefully, but in the most violent explosion the cosmos has to offer. The core is gone, the black hole is born, and now the real fireworks begin. The collapse does not stop. That is the first thing you need to understand. When the iron core of a 40 solar mass star begins to fall inward, there is no mechanism left in the universe's playbook to catch it. Electron degeneracy pressure failed. The electrons themselves have been crushed into protons, forming neutrons and releasing neutrinos that barely slow the collapse on their way out. The temperature has spiked past 10 billion Kelvin. The density has climbed past 1 trillion grams per cubic centimeter, and it is still rising. The core is in free fall, contracting at tens of thousands of kilometers per second, and nothing, not thermal pressure, not quantum mechanics, not the strong nuclear force can stop it. The core is heading toward a threshold, a line in space-time where the rules change, where the physics we understand stops working and something else, something stranger, takes over. That threshold has a name. It is called the Schwarzschild radius, and once the collapsing core crosses it, the core is no longer part of the universe in any meaningful sense. It becomes a black hole. The Schwarzschild radius is not a physical surface. It is not made of anything. You cannot touch it. You cannot see it. It is a mathematical boundary defined by the curvature of space-time itself. The radius depends on mass, only mass. The more massive an object is, the larger its Schwarzschild radius. For our Sun, which weighs about 2 × 10⁻30 kilograms, the Schwarzschild radius is roughly 3 kilometers. That means if you could somehow compress the entire Sun down to a sphere 3 kilometers across, smaller than most cities, the Sun would become a black hole. Space-time around it would warp so severely that light itself could not escape. The Sun is not collapsing, of course. It is held up by fusion. But the number is there, sitting in the equations, waiting. Every object in the universe has a Schwarzschild radius. Earth's is about 9 millimeters. The Moon's is 1/10 of a millimeter. Your body has one too. It is unimaginably small, but it exists. The Schwarzschild radius is the size an object would need to be compressed to in order for its gravity to become so strong that nothing, not even light, could climb back out. For a collapsing stellar core, weighing between 1.5 and 2 solar masses. The Schwarzschild radius is somewhere between 4 and 6 kilometers. That is the target. That is the finish line. The core, which started out thousands of kilometers across, has already contracted to a few hundred kilometers, then a few dozen, then 10. The collapse accelerates. The innermost region of the core, the part that is falling fastest, hits nuclear density first. 2.4 times 10 to the 14th grams per cubic centimeter. At that density, the neutrons are packed together as tightly as the particles inside an atomic nucleus. There is no empty space left. The neutrons are touching, and for a brief moment, neutron degeneracy pressure tries to hold the line. Neutrons, like electrons, are fermions. They obey the Pauli exclusion principle. They resist being stacked on top of each other. In a lighter core, one weighing around 1.4 solar masses, neutron degeneracy pressure would be enough. The collapse would stop. The core would bounce. A neutron star would form, a city-sized ball of neutrons held up by quantum mechanics, and the rebound would send a shockwave tearing through the outer layers of the star. That is what happens in a typical core collapse supernova. The core becomes a neutron star, the star explodes, and the universe gets a new neutron star to add to the catalogue. But this core is heavier. It weighs closer to 2 solar masses, and there is a limit to how much mass neutron degeneracy pressure can support. That limit is not as well defined as the Chandrasekhar limit for electron degeneracy pressure, because the physics at nuclear densities gets complicated fast. The strong nuclear force, which holds protons and neutrons together inside atomic nuclei, starts to play a role. The equation of state, the relationship between pressure and density, becomes uncertain. Nobody knows exactly where the cutoff is. Current estimates put it somewhere between 2 and 2.2 solar masses, maybe higher, maybe lower. Observations of neutron stars have found a few that weigh just over 2 solar masses, which means neutron degeneracy pressure can support at least that much. But the collapsing core of a 40 solar mass star is pushing the limit. And if the core weighs more than the maximum mass neutron degeneracy can hold, the collapse does not stop at nuclear density. It keeps going, past the point where neutrons are touching. Past the point where space-time is merely curved, past the point where general relativity says the curvature becomes infinite. The core crosses the Schwarzschild radius, and it becomes a black hole. The event horizon is what we call the boundary at the Schwarzschild radius. The name is descriptive. An event is something that happens, something you can observe. The horizon is the furthest point you can see. Put them together and you get the edge of observation. The event horizon is the surface beyond which no events can ever be seen by an outside observer. Not because the light is too faint, not because the instruments are not sensitive enough, but because the light never makes it out. Inside the event horizon, space-time is so warped that every direction, every possible path leads inward, toward the center, toward the singularity. There is no outward. Not in any physical sense. You could point a flashlight toward the outside universe and fire a beam of light as hard as physics allows, and the light would still fall inward, not because something is pulling it, but because the geometry of space-time itself has been bent into a shape where outward does not exist. This is where general relativity comes in. General relativity is Einstein's theory of gravity, published in 1916. It replaced Newton's idea of gravity as a force acting at a distance with something more fundamental. Gravity, Einstein said, is not a force. It is the curvature of space-time. Mass and energy warp the fabric of space-time, and objects move along the curved paths that warping creates. The Earth orbits the Sun, not because the Sun is pulling on it, but because the sun's mass has curved space-time in such a way that the Earth's natural straight-line motion through that curved space looks like an ellipse to us. It is a geometric effect, a consequence of living in a universe where space-time is flexible. For weak gravitational fields, the kind we experience on Earth or even near the Sun, general relativity gives almost the same answers as Newton's simpler equations. The differences are tiny, measurable, but tiny. But for strong gravitational fields, the kind you find near neutron stars or black holes, the differences are enormous. Newton's equations break. They give nonsense answers. General relativity is the only tool we have that works. Carl Schwarzschild figured out the math in 1916, just a few months after Einstein published the field equations of general relativity. Schwarzschild was a German physicist and astronomer serving in the German army during World War I. He was stationed on the Russian front, calculating artillery trajectories during the day and working on Einstein's equations at night. He found an exact solution to the equations for the spacetime around a spherical, non-rotating mass. That solution, now called the Schwarzschild metric, describes the geometry of spacetime around any spherical object, stars, planets, black holes, and buried in that solution was a radius where something strange happened. At that radius, the equations said, the curvature of spacetime became so extreme that time stopped, not slowed down, stopped. Schwarzschild sent his solution to Einstein. Einstein was impressed. He presented Schwarzschild's work to the Prussian Academy of Sciences in January 1916. Schwarzschild never saw the impact his work would have. He died a few months later from an illness he contracted on the front. He was 42 years old. His solution outlived him by over a century and became the foundation for our understanding of black holes. The event horizon is not a place where anything physical happens, not to an object crossing it. If you were falling toward a black hole, you would pass through the event horizon without noticing. There would be no wall, no barrier, no sudden change. Locally, space-time would look smooth. You could still see the stars behind you, though they would be distorted and blue-shifted. You could still shine a flashlight and see the beam. You could still breathe, assuming the tidal forces had not already torn you apart. The event horizon is only special from the perspective of an outside observer. To someone watching from a safe distance, you would appear to slow down as you approached the horizon. Your clock would tick slower and slower compared to theirs. Your light would redshift, shifting toward longer and longer wavelengths. You would dim, and as you reached the horizon, you would appear to freeze. Your image would hang there, just outside the horizon, getting redder and dimmer but never quite crossing. That is because the light you emit as you cross the horizon takes longer and longer to climb back out of the gravitational well. The light emitted just before you cross takes an infinite amount of time to escape. So to an outside observer, you never fall in. You just fade away, asymptotically approaching the horizon, your image frozen at the threshold forever. Meanwhile, from your perspective, nothing special happens. You cross the horizon in a finite amount of your own time. You keep falling. And a short while later, you hit the singularity and stop existing. The singularity is where the collapse ends, not at the event horizon. The horizon is just the boundary. Inside the horizon, the collapse continues. The core keeps shrinking. The density keeps climbing. And according to general relativity, there is no force in the universe that can stop it. The core contracts to a point, not a very small sphere, a point, zero radius, zero volume, infinite density. That is what the equations say. Every bit of mass that fell into the black hole, every proton, every neutron, every particle, gets compressed into a single geometric point at the center. A singularity. The word comes from mathematics. A singularity is a place where a function becomes infinite or undefined. In this case, the function is space-time curvature. At the singularity, the curvature of space-time becomes infinite. The equations of general relativity, which worked perfectly everywhere else, break down. They give infinity as an answer. And infinity is not a number you can work with. It is a sign that something is wrong. Either the theory is incomplete or the question you are asking does not make sense. Most physicists believe the singularity is not real. Not in the sense that there is actually a point of infinite density sitting at the center of every black hole. More likely, the singularity is a placeholder, a signal that general relativity is not the final word. At the scales and densities we are talking about, quantum mechanics should matter. And general relativity does not include quantum mechanics. It is a purely classical theory. A full theory of quantum gravity, which does not yet exist, would probably smooth out the singularity into something finite, maybe a region of extremely high but not infinite density, maybe something even stranger. But until someone figures out quantum gravity, we are stuck with general relativity. And general relativity says singularity. The singularity is hidden behind the event horizon, always. There is a theorem in general relativity called the cosmic censorship hypothesis, which says that singularities cannot exist without event horizons to cover them. Nature, the hypothesis claims, abhors a naked singularity. Every singularity must be clothed in an event horizon, hidden from the outside universe. This has never been proven rigorously, but it holds in every case we have checked. If the core is heavy enough to form a singularity, it is also heavy enough to curve space-time into an event horizon that traps the singularity inside. The black hole is born, and the universe is spared the embarrassment of having to display a region of infinite density in plain view. The black hole that forms at the center of a collapsing 40 solar mass star weighs somewhere between 1.5 and 2 solar masses. That mass is packed into a region smaller than a city. The event horizon, the boundary of the black hole, has a radius of 4 to 6 kilometers. For comparison, Manhattan is about 20 kilometers long. You could fit this entire black hole inside Central Park and have room left over. But do not let the size fool you. The gravitational field near the event horizon is strong enough to warp space-time into knots. If you were hovering just outside the horizon, you would need to accelerate at millions of Gs just to stay in place, millions of times the acceleration due to gravity on Earth. Your rocket engines would need to produce thrust equivalent to a significant fraction of the speed of light just to keep you from falling in, and the tidal forces would be lethal long before you got that close. Tidal forces are the difference in gravitational pull across an object. Your feet, being closer to the black hole than your head, would feel a stronger pull. For a black hole this size, the tidal forces a few hundred kilometers above the event horizon would be strong enough to stretch a human body into a thin strand of atoms. Astronomers call this spaghettification. It is not a joke, it is a real effect. You would be turned into spaghetti, literally. Stretched lengthwise, compressed sideways, pulled apart molecule by molecule, until you were a stream of ionized plasma spiraling inward. The black hole is spinning, probably. Every star spins. The sun rotates once every 27 days. Massive stars tend to spin faster. And when the core collapses, conservation of angular momentum kicks in. Just like a figure skater pulling in their arms to spin faster, the collapsing core speeds up as it shrinks. By the time it crosses the event horizon, it could be spinning at a significant fraction of the speed of light. A spinning black hole is described by a different solution to Einstein's equations, called the Kerr metric. discovered by Roy Kerr in 1963. The Kerr solution is more complicated than the Schwarzschild solution. The event horizon is not a perfect sphere. It bulges at the equator, and there is a second surface outside the event horizon called the ergosphere. Inside the ergosphere, space-time itself is dragged around the black hole. You cannot stand still. You are forced to move in the direction of the black hole's rotation. You can still escape. You are outside the event horizon, but you cannot avoid being swept along. The ergosphere is where some of the wildest physics happens. In principle, you could extract energy from a spinning black hole by dropping material into the ergosphere and using the dragging of spacetime to accelerate it back out. The process is called the Penrose mechanism, and it might be responsible for some of the most energetic jets we see in the universe. But we are getting ahead of ourselves. The jets come later. Right now, the black hole has just formed. The event horizon has just appeared. And the singularity, whatever it is now hidden inside, inaccessible to observation forever. Here is the thing that makes black holes so conceptually difficult. You cannot see inside them, ever. The event horizon is a one-way boundary. Information can cross inward. Nothing crosses outward. Not light, not particles, not information of any kind. That means we cannot observe the singularity. We cannot test whether it is really infinite or whether quantum effects smooth it out. We cannot measure the density or the temperature or the structure of the core once it crosses the horizon. It is gone, cut off from the rest of the universe. All we can observe is the event horizon itself and the effects of the black hole's gravity on the matter around it. The black hole could have a complicated structure inside, or it could be completely empty except for the singularity. We would never know the difference. The event horizon is an information barrier, a wall in space-time that divides what we can know from what we can never know. And that is deeply unsatisfying to physicists who are used to being able to, in principle, measure anything if they build the right instrument. The mass of the black hole is measurable from the outside. If you watch how matter moves near the black hole, you can infer its mass from the orbital speeds and trajectories. The spin is measurable too, though it is harder. You have to look at how space-time is dragged around the black hole and work backward from the geometry. The charge, if the black hole has any, is also measurable in principle, though most black holes are thought to be electrically neutral because matter tends to be neutral on average. So we can measure three properties: mass, spin, and charge, and that is it. Everything else about the black hole, every detail of what fell in, every bit of structure the core had before it collapsed, is lost. There is a theorem in black hole physics called the no-hair theorem. It says that black holes have no hair, meaning no extra features, no distinguishing marks. Two black holes with the same mass, spin, and charge are identical. They are indistinguishable. Even if one formed from the collapse of an iron core and the other formed from a collapsing cloud of hydrogen, once they have settled down, they look the same. The information about what they were made of is gone, erased, hidden behind the event horizon where nothing can ever retrieve it. This bothers physicists a lot, because it seems to violate a principle called unitarity, which says information cannot be destroyed. The debate over whether black holes destroy information or preserve it in some hidden form is one of the biggest unsolved problems in theoretical physics. Stephen Hawking spent decades arguing both sides of that question. He eventually conceded that information is probably preserved somehow, but nobody knows how. The black hole is not stable, not in the long term. In 1974, Hawking showed that black holes emit radiation, not from inside the event horizon, from just outside it. Quantum mechanics allows particle-antiparticle pairs to spontaneously pop into existence out of the vacuum, borrowing energy from empty space for a brief moment before annihilating each other and paying the energy back. Normally, these virtual particles appear and disappear so quickly that they have no observable effect. But near the event horizon of a black hole, something strange can happen. One particle of the pair can fall into the black hole while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. To an outside observer, it looks like the black hole is radiating, Hawking radiation. The process is incredibly slow for a stellar mass black hole. The temperature of the radiation is inversely proportional to the mass. A black hole weighing 2 solar masses has a temperature of about 30 billionths of a Kelvin. That is colder than the cosmic microwave background, far colder. So the black hole absorbs more energy from the background radiation of the universe than it loses through Hawking radiation. It grows instead of shrinking. But in the far future, after the universe has expanded and cooled, and the cosmic microwave background has redshifted into nothingness, the black hole will start to lose mass, slowly at first, then faster as it gets lighter and hotter. Eventually, in something like 10 to the 67 years, the black hole will evaporate completely in a final burst of radiation. 10 to the 67 years is a number so large it makes the current age of the universe look like a rounding error. The universe is about 14 billion years old. 10 to the 67 is a 1 followed by 67 zeros. By the time this black hole evaporates, every star in the universe will have burned out, every galaxy will have dissipated, and the universe will be a cold, dark, nearly empty void. But the math says it will happen, eventually. For now, though, the black hole is newborn. It formed less than a second ago. The collapse took a fraction of a second. The event horizon snapped into existence the moment the core shrank below the Schwarzschild radius. And now the black hole is sitting at the center of what used to be a star, surrounded by the infalling outer layers of the core that have not reached the horizon yet. Those layers are still collapsing inward, still heating up, still releasing energy, and that energy has nowhere to go. The outer layers, the shells of silicon and oxygen and neon and carbon and helium and hydrogen, are still sitting there, thousands of kilometers above the event horizon, still fusing, still glowing, completely unaware that the core they were sitting on has disappeared. But they are about to find out. Because the rebound from the core collapse, or in this case the accretion of matter onto the newborn black hole, is about to send a shockwave and a pair of jets screaming outward at nearly the speed of light. The star is not exploding yet, but the fuse has been lit, and the explosion, when it comes, will be visible across half the universe. The black hole is 1 second old, maybe 2. The core collapsed. The event horizon snapped into existence. The singularity formed, whatever that really means, hidden forever behind a wall in space-time that nothing can ever cross outward. And now the black hole is sitting there, in the middle of what used to be a star, surrounded by the wreckage of the collapse, thousands of solar masses of star above it. Shells of silicon and oxygen and neon and carbon still burning, still glowing, still pouring energy outward, and beneath all of that, falling inward at tens of thousands of kilometers per second, the outer layers of the iron core. Matter that did not quite make it into the black hole during the initial collapse. Matter that is still on its way in. That matter is about to do something extraordinary. It is about to scream. The infalling material does not fall straight into the black hole. It cannot. Not if it has any angular momentum at all. And it does. Every star rotates. The Sun spins once every 27 days. Massive stars spin faster. When the core collapses, that rotation speeds up dramatically. Conservation of angular momentum. The same reason a figure skater spins faster when they pull their arms in. The collapsing core was rotating slowly when it was thousands of kilometers across. By the time it shrinks to a few kilometers, it is spinning at a significant fraction of the speed of light, and the material falling toward it carries that rotation with it. It cannot fall straight in. The rotation forces it into a spiral, an orbit, and as more and more material piles up in that orbit, it forms a disk, an accretion disk, a swirling, churning, superheated disk of matter orbiting the black hole at speeds that would make a planetary orbit look like a leisurely stroll. Accretion disks are not unique to black holes. They form around any object that is pulling in matter faster than that matter can fall straight inward. White dwarfs in binary systems can have accretion disks, neutron stars too. Even young stars, still forming from clouds of gas, are surrounded by protoplanetary disks that eventually coalesce into planets. But the accretion disk around a newborn black hole, a black hole that just formed from the collapsed core of a 40 solar mass star, is something else entirely. This is not a gentle disk of gas and dust quietly condensing into rocky planets over millions of years. This is a disk of ionized plasma, heated to billions of degrees, orbiting at a significant fraction of the speed of light, packed so densely that the pressure alone could crush a neutron star. The disk glows, not with visible light, with X-rays, gamma rays, radiation so energetic that it would sterilize anything within light years if it were not trapped inside the collapsing star. The material in the disk is not sitting still, it is spiraling inward, slowly compared to the orbital speeds, but inexorably. Friction between particles in the disk converts orbital energy into heat. The inner edge of the disk, closest to the black hole, is the hottest part. Temperatures there can reach 100 billion Kelvin, higher than the core of any star. The matter glows white-hot with thermal radiation, but most of the energy is radiated away as high-energy photons that slam into the surrounding gas and heat it even further. The disk is feeding the black hole. Every second, a fraction of a solar mass of material crosses the event horizon. Some of that mass gets converted into energy, not through fusion, through gravity. When matter falls into a black hole, it releases gravitational potential energy, a lot of energy, up to about 40% of the rest mass energy, depending on how fast the black hole is spinning. For comparison, fusion converts about 0.7% of the rest mass into energy. Accretion onto a black hole is one of the most efficient energy conversion processes in the universe, more efficient than fusion, more efficient than chemical reactions, more efficient than anything except matter-antimatter annihilation. But here is the thing. Not all of that energy falls into the black hole. Most of it does, but some of it escapes, and the way it escapes is through the jets. This is where the physics gets strange and beautiful and terrifying. Because the mechanism that launches jets from black holes is one of the most violent processes in nature, and it is powered by something invisible: magnetic fields. Magnetic fields exist everywhere in the universe. The Earth has one, the Sun has one. Every star, every planet with a molten core, every spinning charged object generates a magnetic field. The collapsing core of a massive star carries magnetic fields with it. Weak fields initially, but as the core contracts, those fields get compressed, squeezed tighter and tighter, and a magnetic field that gets compressed gets stronger, a lot stronger. The strength of a magnetic field scales with the inverse square of the distance. Shrink the core by a factor of 10, and the field strength increases by a factor of 100. Shrink it by a factor of 1,000, and the field increases by 1,000,000. By the time the core has collapsed into a black hole and the accretion disk has formed, the magnetic field threading through that disk is not weak. It is the strongest magnetic field in the local universe. Trillions of times stronger than the field around the Earth. Strong enough to rip atoms apart. Strong enough to twist space-time itself. The magnetic field lines in the accretion disk do not just sit there, they move. They get dragged along with the rotating plasma. The inner part of the disk rotates faster than the outer part. That is how orbital mechanics works. Closer orbits are faster. So the magnetic field lines anchored in the plasma get wound up, twisted, stretched. Imagine taking a rubber band and twisting it. At first, it is easy, but the more you twist, the harder it gets. The rubber band stores energy in the twist. Magnetic fields work the same way. The more you twist them, the more energy they store. And in the accretion disk around a newborn black hole, the fields are being twisted thousands of times per second. The energy builds, and eventually it has to go somewhere. The fields do not twist uniformly across the disk. They get tangled, knotted. And when magnetic field lines with opposite polarities come close enough together, they reconnect, magnetic reconnection. It is the same process that powers solar flares on the Sun, except this is not happening on the surface of a star at 6,000 Kelvin. This is happening in a disk of plasma at 100 billion Kelvin, threaded with fields strong enough to tear electrons away from their nuclei just by proximity. When reconnection happens in that environment, it releases energy, a lot of energy, instantaneously. That energy accelerates particles, electrons, protons, ions, anything with a charge. The particles get flung outward along the magnetic field lines at relativistic speeds, speeds approaching the speed of light. And because the magnetic fields near the black hole are strongest along the rotation axis, where the disk is thinnest, the particles get channeled, funneled, collimated into two narrow beams shooting out along the poles of the black hole. One jet pointing north, one pointing south, both moving at 99% the speed of light or faster. The jets are not made of light, they are made of matter, plasma, ionized gas, electrons and protons and heavier ions stripped of their electrons, moving so fast that their mass increases due to relativistic effects. At 99% the speed of light, a particle's relativistic mass is about 7 times its rest mass. At 99.9%, it is about 22 times. At 99.99%, over 70 times. The faster the particles move, the heavier they get, and the more energy they carry. The jets coming out of a collapsing stellar core can carry away a significant fraction of the total energy released by the collapse. We are talking about energies on the order of 10 to the 51 ergs. That is a 1 followed by 51 zeros. For comparison, the Sun outputs about 4 times 10 to the 33 ergs per second. The jets from a collapsing stellar core, in the span of a few seconds, release more energy than the Sun will produce over its entire 10 billion year lifetime. And that energy is concentrated into 2 beams narrower than the width of the Earth. The mechanism that launches these jets is still not completely understood. Astrophysicists have 2 main theories, and both of them are probably correct. They are not mutually exclusive. The first theory is called the Blandford-Znajek mechanism, named after Roger Blandford and Roman Znajek, who worked out the math in the 1970s. The idea is that the spinning black hole itself powers the jets. Not by emitting anything from inside the event horizon, that is impossible, but by extracting rotational energy from the space-time around the event horizon. Remember the ergosphere, the region outside the horizon where space-time is dragged around by the black hole's spin. Magnetic field lines threading through the ergosphere get twisted by that dragging motion. The twist stores energy, and that energy can be extracted by particles moving along the field lines. The particles do not need to fall into the black hole. They can be accelerated outward along the field lines, stealing energy from the black hole's rotation as they go. The black hole spins down slightly, the particles speed up, energy is conserved, and the jet is launched. The Blandford's-Najek mechanism works best for rapidly spinning black holes. The faster the spin, the more energy you can extract. And a black hole that just formed from a collapsing stellar core is probably spinning very fast, close to the maximum allowed by general relativity. The second theory focuses on the accretion disk itself. The disk is not a passive structure, it is turbulent, chaotic. Magnetic fields in the disk get tangled and twisted by the turbulence, and those twisted fields exert forces on the plasma. The magnetorotational instability, discovered in simulations in the 1990s, shows that magnetic fields in a rotating disk naturally amplify and create turbulence that drives matter inward while simultaneously flinging some of it outward along the field lines. The outward flung material gets channeled by the fields into jets. The process is self-sustaining. As long as matter is falling into the disk, the turbulence continues, the fields continue to twist, and the jets continue to launch. This mechanism does not require a spinning black hole. It works even if the black hole is not rotating. But it works better if the black hole is spinning because the spin helps to organize the magnetic fields into a more coherent structure. Both mechanisms are probably happening at the same time. The black hole's spin powers part of the jet through the Blandford's-Najek mechanism. The accretion disk powers another part through magnetohydrodynamic processes. The two effects add together. The result is a pair of jets that carry away enormous amounts of energy, far more than either mechanism could produce alone, and the jets are collimated, tightly focused. The opening angle of the jets, the angle between the central axis and the edge of the jet, is only a few degrees, sometimes less than 1 degree. For a jet that can extend for thousands or millions of light years, that is an absurdly narrow beam. It is like shooting a laser pointer at the moon and hitting a target the size of a coin. Except the laser pointer is a stream of plasma moving at 99.9% the speed of light, and the moon is a galaxy halfway across the universe. The collimation is achieved by the magnetic fields. The fields act like a nozzle. Picture a garden hose. If you pinch the end of the hose, the water squirts out faster and in a narrower stream. The magnetic fields around the black hole do the same thing to the plasma. They squeeze it, confine it, force it into a narrow cone along the rotation axis. The fields are strongest near the black hole, where the collimation is tightest. Farther out, the fields weaken and the jet starts to spread. But even thousands of light years away, the jet is still recognizably a jet. A coherent beam of plasma, glowing with synchrotron radiation, plowing through the interstellar medium at relativistic speeds. Synchrotron radiation is what happens when charged particles, usually electrons, are accelerated in a magnetic field. The acceleration causes the particles to emit radiation. The frequency of the radiation depends on how fast the particles are moving and how strong the magnetic field is. For relativistic particles in strong fields, the radiation peaks in the radio part of the spectrum. That is why jets are so bright in radio observations. They are lousy with synchrotron radiation. Every electron spiraling along a magnetic field line is radiating, and there are trillions of electrons in the jet. The combined glow is so bright that jets from distant galaxies, galaxies billions of light-years away, can be detected with radio telescopes on Earth. The jets are beacons, advertisements of the black hole's feeding frenzy, visible across the entire observable universe. The jets do not last forever. They are powered by the accretion disk, and the accretion disk is powered by the infalling matter. Eventually, the star runs out of matter to fall in. The outer layers get blown away by the explosion, which we will get to. The accretion rate drops, the disk thins, the magnetic fields weaken, the jets sputter out. The whole process, from the moment the jets first ignite to the moment they shut off, lasts anywhere from a few seconds to a few minutes, maybe longer if the black hole manages to capture additional material from the surrounding environment. But for a collapsing stellar core, the timescale is short. The jets are a brief, violent burst of energy, a scream, and then silence. But during those few seconds, the jets are the most powerful concentrated energy source in the universe. Nothing else comes close, not supernovae. Not gamma-ray bursts, though, as we will see, gamma-ray bursts are produced by these same jets. Not quasar cores, nothing. The energy flux in a relativistic jet, the amount of energy passing through a given area per second, is so high that if you could somehow put your hand in the path of the jet, your hand would not just burn, it would cease to exist. The radiation alone would ionize every atom in your hand before the plasma even arrived. And when the plasma did arrive, traveling at 99.9% the speed of light, it would not hit you. It would pass through the space where you used to be and keep going, completely unaffected. You would be gone, vaporized, converted into a brief puff of radiation that would be lost in the noise of the jet itself. The jets punch through the star. This is important. The star is still there. The core has collapsed. The black hole has formed. The jets have launched. But the rest of the star, the thousands of solar masses of hydrogen and helium and carbon and oxygen and silicon, are still sitting above the black hole, still glowing, still held together by gravity. The jets have to get through all of that to escape into space. And they do. The jets carry so much energy, so much momentum, that they bore through the overlying layers like a drill through butter. The plasma, moving at near light speed, slams into the slower-moving gas above it. The collision heats the gas to billions of degrees. The gas explodes outward. A shock wave forms, propagating ahead of the jet, clearing a path. The jet follows behind, carving a tunnel through the star. The tunnel is not smooth, it is turbulent, chaotic. Eddies and vortices form along the edges where the fast-moving jet plasma mixes with the slower stellar material. But the central beam stays coherent, the magnetic fields hold it together. And within seconds, the jet breaks through the surface of the star and erupts into space. When the jet breaks through, it does not slow down. It is already moving at 99% the speed of light or faster. Space is a much better vacuum than the inside of a star. There is nothing to stop the jet. It just keeps going, plowing through the interstellar medium, which is thin but not empty. A few atoms per cubic centimeter on average. The jet hits those atoms head-on at relativistic speeds. The collisions produce more synchrotron radiation, more heat, more shock waves. The jet sweeps up the interstellar gas and pushes it aside, creating a bubble of hot, low-density plasma around the star. That bubble expands. It can grow to be light years across. And the jet keeps going, sometimes for thousands of parsecs, until it finally runs out of energy and dissipates into the background noise of the galaxy. The jets are not uniform. They flicker, they vary in brightness. The accretion disk is turbulent, so the amount of material falling into the black hole fluctuates. More material means more energy in the jets. Less material means the jets dim. The variations happen on short time scales, milliseconds to seconds. Observers watching the jets, if they could somehow survive close enough to see them, would see them pulse, brightening and dimming rhythmically, almost like a heartbeat. Except the heartbeat is powered by a black hole eating a star, and each pulse carries more energy than humanity has used in its entire history. The jets also precess, wobble. The accretion disk is not perfectly aligned with the black hole's spin axis. It is tilted slightly, and that tilt causes the jets to trace out a cone in space as the disk wobbles. The lens-Thirring effect, a prediction of general relativity, says that the spinning black hole drags space-time around it in such a way that a tilted disk will precess. The disk gradually aligns with the black hole's equator, but the process takes time. During that time, the jets sweep across the sky like searchlights. If you were watching from a safe distance, you would see the jets trace out a spiral pattern. And if you were unlucky enough to be in the path of the jet as it swept across your location, you would see nothing. You would be dead before the light reached your eyes. The energy in the jets comes from the gravitational well of the black hole. Every kilogram of matter that falls into the accretion disk releases energy as it spirals inward. Some of that energy heats the disk, some of it radiates away as light, and some of it gets funneled into the jets. The efficiency depends on how fast the black hole is spinning and how strong the magnetic fields are. In the best cases, up to 40% of the infalling rest mass energy can be extracted and channeled into the jets. That is an absurd number. For comparison, the most efficient rocket engines we have built on Earth convert less than 0.1% of their fuel into useful kinetic energy. Nature, when it wants to, can do vastly better. And a black hole with a strong magnetic field and a fast rotation rate is nature at its most efficient. There is something almost elegant about the whole process. The star collapses. The core forms a black hole. The magnetic fields get amplified. The fields channel energy into jets. The jets punch through the star and escape into space. Every step follows from the laws of physics. Nothing is random, nothing is arbitrary. Given the initial conditions, a 40 solar mass star with a rotating core and a magnetic field, the outcome is determined. The jets will form, they will launch. They will carry away enormous amounts of energy, and they will be visible across the universe. The only question is which direction they are pointing, because the jets are narrow. If they are pointing toward Earth, we see a gamma-ray burst, the brightest electromagnetic event in the universe. A flash of radiation so intense that it outshines every other source in the sky combined. If the jets are pointing away from Earth, we see nothing, or almost nothing. Maybe a faint supernova weeks later when the outer layers of the star finally explode. But the jets themselves, the relativistic beams screaming outward at 99.9% the speed of light, are invisible to us, not because they are dim, but because they are aimed somewhere else. A laser pointer is only bright if you are looking at the beam head-on. From the side, you see nothing. The jets work the same way, and that brings us to the next chapter of this story. Because the jets do not just carry energy, they carry information. Information about the most violent death in the universe. When those jets are aimed at Earth, when we are unlucky enough, or lucky enough depending on your perspective, to be looking down the barrel of one of those beams, we detect something extraordinary, a gamma-ray burst. A flash of the highest energy light in the electromagnetic spectrum, lasting anywhere from a fraction of a second to a few minutes, releasing more energy than the sun will produce in its entire lifetime. For decades, astronomers had no idea what was causing these bursts. They knew they were coming from distant galaxies. They knew they were incredibly energetic, but they did not know the mechanism. Not until they started putting together observations of supernovae and gamma-ray bursts and realizing that some of them, the long-duration ones, were happening at the same time and in the same place. The bursts were coming from collapsing stars, from the jets, and the model that explained it, the model that tied everything together, was called the Collapsar model. That is where we are going next. The jets are moving at 99% the speed of light, maybe faster. They have punched through the collapsing star, bored a tunnel through thousands of kilometers of stellar material, and erupted into space like a drill through wet paper. The black hole at the center is feeding. The accretion disk is glowing. The magnetic fields are twisted into knots, so tight they could slice space-time itself. And the jets, those twin beams of plasma and energy screaming outward along the rotation axis, are about to announce their existence to the rest of the universe. Not with a whisper, with a scream. A flash of light so bright, so energetic, that it will outshine every other source in the sky combined. A gamma-ray burst. Gamma-ray bursts are the brightest explosions in the universe, full stop. Nothing else comes close. Not supernovae, not quasar flares, not the collision of neutron stars, though that produces its own kind of burst. A gamma-ray burst, when it goes off, can release more energy in a few seconds than the sun will produce over its entire 10 billion-year lifetime. Some bursts release more energy than that, a lot more. The most energetic gamma-ray bursts ever detected have unleashed the equivalent of converting several solar masses directly into pure radiation. That is not a metaphor. That is the actual energy budget. Several times the mass of the sun, converted into light, released in a matter of seconds, and beamed across the universe in a cone so narrow that most of the cosmos never sees it. If you are not in the path of the beam, you miss the show entirely. If you are in the path, you see the most violent event the universe has to offer. The story of how we discovered gamma-ray bursts is almost as strange as the bursts themselves. It starts in the late 1960s. The Cold War was in full swing. The United States and the Soviet Union had just signed the Partial Nuclear Test Ban Treaty, an agreement that prohibited nuclear weapons tests in the atmosphere, in space, and underwater. The treaty allowed underground tests, but it banned the obvious ones, the ones you could see from orbit. And the United States, not trusting the Soviets to actually follow the rules, decided to watch them. The military launched a series of satellites called Vela. The name means watchman in Spanish. The Vela satellites carried instruments designed to detect the gamma-ray and X-ray signatures of nuclear explosions. If the Soviets detonated a bomb in space, Vela would see it. That was the plan. Vela worked. It detected gamma rays, lots of them, but they were not coming from Soviet nuclear tests. They were coming from space, deep space. The detections started showing up in the data in the late 60s, but nobody said anything. The program was classified, the satellites were military hardware, and the gamma-ray signals did not match the profile of a nuclear explosion. They were too short, too energetic, and they were not coming from Earth or anywhere near Earth. They were coming from random directions. No pattern, no repeats, just brief, intense flashes of the highest energy light in the electromagnetic spectrum, arriving from different parts of the sky at a rate of about one per day. The first public announcement came in 1973. A team of scientists from Los Alamos National Laboratory, led by Ray Klebsadel, published a paper in the Astrophysical Journal describing 16 gamma-ray events detected by the Vela satellites between 1969 and 1972. They called them gamma-ray bursts. The name stuck. The bursts were a complete mystery. Nobody knew what was causing them. Nobody knew how far away they were. The only thing anyone knew for sure was that they were real, they were energetic, and they were coming from outside the solar system, possibly from outside the galaxy. The debate over the distance scale lasted for more than 2 decades. Some astronomers thought the bursts were coming from nearby objects in the Milky Way, neutron stars maybe, or some kind of exotic compact object we had not discovered yet. Others argued that the bursts had to be coming from distant galaxies. The energy required for a nearby source was manageable, a few times 10 to the 39 ergs, bright but not absurd. But if the bursts were at cosmological distances, billions of light-years away, the energy budget exploded. You would need 10 to the 51 ergs or more. 10 to the 51 ergs is a number so large that it stops making sense in any human context. It is more energy than a supernova releases. It is more energy than most galaxies produce in a year, and it all has to come out in a few seconds. Nobody could figure out what kind of object could do that. The distance question got answered in 1997. NASA launched a satellite called the Compton Gamma Ray Observatory. One of its instruments, the Burst and Transient Source Experiment, detected thousands of gamma-ray bursts over the course of its 9-year mission. The bursts were distributed uniformly across the sky, no clustering. No preference for the galactic plane, that ruled out nearby sources. Nearby objects in the Milky Way would cluster along the plane of the galaxy. These bursts did not. They were isotropic, coming from every direction. That meant they were either very close, within the solar system, which made no sense, or very far away, cosmological distances, outside the galaxy. In 1997, the Bepo-Sax satellite detected a gamma-ray burst and, for the first time, pinpointed its location accurately enough that ground-based telescopes could follow up. They found an optical afterglow, a fading glow of light in the visible spectrum, sitting in a distant galaxy. The redshift of that galaxy put it billions of light-years away. The debate was over. Gamma-ray bursts were cosmological, and that meant the energy budget was real. 10 to the 51 ergs, maybe more. Gamma-ray bursts come in 2 flavors, short duration and long duration. The dividing line is 2 seconds. Short bursts last less than 2 seconds, sometimes less than 1/10 of a second. Long bursts last longer than 2 seconds, sometimes much longer. The longest burst ever detected lasted more than an hour, though most long bursts average around 30 seconds. The 2 types are not just different in duration, they are different in origin. Short bursts are caused by the merger of 2 neutron stars, or a neutron star and a black hole. When 2 neutron stars spiral into each other and collide, they release a tremendous amount of energy in the form of gravitational waves, neutrinos, and electromagnetic radiation. The merger also produces a gamma-ray burst, a short one. The burst lasts less than 2 seconds because the event is over quickly. The neutron stars merge, the gamma rays are emitted, and then it is done. We have detected gravitational waves from neutron star mergers. The first confirmed detection was in August 2017. LIGO and Virgo, the gravitational wave observatories, picked up the signal, and less than 2 seconds later, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same location. It was a smoking gun. Proof that at least some gamma-ray bursts are caused by neutron star mergers. Long-duration gamma-ray bursts are different. They are not caused by mergers. They are caused by the collapse of massive stars, specifically the collapse of stars massive enough to form black holes. This is the Collapsar model. The word Collapsar is shorthand for collapsing star. It is not a technical term, it is jargon. But it is the best word we have for what is happening. A massive star, something in the range of 25 to 50 solar masses, reaches the end of its life. The core runs out of fuel, the iron core forms, the core collapses, a black hole is born, an accretion disk forms around the black hole. Magnetic fields thread through the disk, and relativistic jets are launched along the rotation axis. Those jets punch through the star and escape into space, and when they do, they produce a gamma-ray burst. The Collapsar model was proposed in the late 1990s by Stan Woosley, an astrophysicist at the University of California, Santa Cruz. Woosley and his colleagues ran computer simulations of collapsing massive stars and found that under the right conditions, the collapse could produce jets, powerful jets. Jets moving at more than 99% the speed of light. And those jets, when they broke through the surface of the star, could produce a flash of gamma rays bright enough to be detected across the universe. The model explained a lot. It explained why long gamma-ray bursts were associated with star-forming regions. Young, massive stars are born in those regions. It explained why gamma-ray bursts were so energetic. The collapse of a stellar core into a black hole releases an absurd amount of energy, and it explained why the bursts were so short. The jets only last as long as the accretion disk is feeding the black hole. Once the disk runs out of material, the jets shut off. The whole process takes a few seconds to a few minutes, and then it is over. The key to the Collapsar model is the jets. Without jets, you do not get a gamma-ray burst. You just get a regular supernova. Or maybe not even that. If the core collapses directly into a black hole without producing jets, the explosion might fail entirely. The outer layers of the star just fall into the black hole. No explosion, no supernova, just a star that quietly disappears, leaving a black hole behind. Astronomers call these failed supernovae. We have seen them. Stars that were there one day and gone the next, with no explosion in between. But if the collapse produces jets, everything changes. The jets carry so much energy that they can power the explosion. They bore through the star, heating the surrounding gas, driving shock waves outward. The outer layers of the star get blown away. The explosion is not spherical. It is bipolar. Most of the energy goes into the jets, but the shock waves driven by the jets push the rest of the star outward. The result is a hypernova, a supernova that is even more energetic than a normal core collapse supernova. And at the moment the jets break through the surface of the star, the gamma-ray burst goes off. Here is how it works. The jets are moving at 99% the speed of light or faster, relativistic speeds. At those speeds, the physics gets weird. Time dilation kicks in. The material in the jet experiences time more slowly than the surrounding universe. Distances contract. The jet itself, from its own perspective, is much shorter than it looks to an outside observer, and the radiation it emits gets beamed forward. This is called relativistic beaming. Imagine a flashlight. If the flashlight is stationary, the light spreads out in all directions. But if the flashlight is moving toward you at close to the speed of light, the light gets concentrated into a narrow beam pointing in the direction of motion. The faster the flashlight moves, the narrower the beam. At 99% the speed of light, the beam is only a few degrees wide. At 99.9%, it is less than a degree. The jets from a collapsing star are moving at those kinds of speeds, and the gamma rays they emit get beamed forward into a cone so narrow that you can only see the burst if you are looking almost directly down the barrel of the jet. That is why gamma ray bursts are so bright. Not because they are releasing more total energy than anything else in the universe. Some of them are, but not all. The brightness comes from the beaming. All the energy that would normally spread out in all directions gets focused into a narrow cone. If you are in that cone, you see an incredibly bright flash. If you are outside the cone, you see nothing, or almost nothing. Maybe a faint supernova weeks later. But the gamma-ray burst itself is invisible to you. This also means that for every gamma-ray burst we detect, there are hundreds of others that we miss because the jets are not pointing toward Earth. The true rate of gamma-ray bursts in the universe is much higher than the observed rate. We only see the ones aimed at us. The rest go off unnoticed, their light streaking across the cosmos in directions we will never look. The gamma rays themselves are produced by a process called synchrotron emission. Electrons in the jet, moving at relativistic speeds, spiral around magnetic field lines. The acceleration causes them to emit radiation. At the speeds and magnetic field strengths we are talking about, the radiation peaks in the gamma-ray part of the spectrum. Gamma rays are the highest energy photons in the electromagnetic spectrum, higher energy than X-rays, higher than ultraviolet, higher than visible light. A gamma-ray photon can have an energy of 1,000,000 electron volts or more. For comparison, a photon of visible light has an energy of about 2 electron volts. Gamma rays are hundreds of thousands of times more energetic, and a gamma-ray burst can emit 10 to the 51 ergs of that radiation in a few seconds. That is a 1 followed by 51 zeros. In joules, it is about 10 to the 44 joules. For comparison, the entire energy output of the Sun over its 10 billion-year lifetime is about 10 to the 44 joules. A gamma-ray burst releases that much energy in 10 seconds. The electromagnetic spectrum is a way of organizing light by its energy or wavelength. At the low energy end, you have radio waves, long wavelength, low energy, then microwaves, then infrared, then visible light, which occupies a tiny sliver of the spectrum between red and violet, then ultraviolet, then X-rays, and at the very top, the highest energy end, you have gamma rays. Gamma rays have wavelengths shorter than the size of an atomic nucleus. They are invisible to human eyes. They do not interact with the lenses or mirrors in optical telescopes. You cannot reflect gamma rays the way you can reflect visible light. To detect gamma rays, you need specialized instruments, detectors made of materials that absorb gamma rays and convert them into a signal that can be measured: lead, tungsten, cesium iodide. These materials stop gamma rays and produce a flash of lower energy light or an electrical signal that can be recorded. Gamma-ray telescopes do not have mirrors. They have detectors, and those detectors have to be in space. The Earth's atmosphere is opaque to gamma rays. A gamma-ray photon entering the atmosphere from space will collide with an air molecule and get absorbed before it makes it halfway to the ground. That is a good thing for life on Earth. Gamma rays are ionizing radiation. They can strip electrons away from atoms and break chemical bonds. A strong dose of gamma rays will kill you. The atmosphere protects us, but it also means that if you want to detect gamma rays from space, you have to put your detector above the atmosphere, on a satellite, in orbit. The Fermi Gamma Ray Space Telescope, launched in 2008, is one of the primary instruments for detecting gamma-ray bursts. It carries two main instruments: the gamma-ray burst monitor, which detects bursts across the entire sky, and the Large Area Telescope, which observes the highest energy gamma rays. Between them, Fermi detects about 240 gamma-ray bursts per year. Not all of them are long-duration bursts from collapsing stars. Some are short bursts from neutron star mergers. But the long ones, The ones that last more than 2 seconds, those are the ones tied to the Collapsar model, the ones tied to black hole formation, the ones tied to the death of massive stars. When a gamma-ray burst goes off, the gamma rays are the first thing we detect. They travel at the speed of light. Nothing is faster. The burst arrives at Earth as a flash of gamma rays lasting anywhere from a fraction of a second to several minutes. The intensity can vary wildly during the burst. Some bursts are smooth, a single peak. Others are chaotic, multiple peaks, flares, flickering. The variability tells us something about the source. A smooth burst suggests a relatively stable jet. A chaotic burst suggests turbulence. Instabilities in the accretion disk. Variations in the magnetic field. The jet is not a steady beam, it is flickering, pulsing. The black hole is feeding erratically, and that erratic feeding shows up in the gamma-ray light curve. The light curve is a graph of brightness over time. For a gamma-ray burst, the light curve can be incredibly complex. A series of spikes and dips, each one representing a surge of energy from the jet. Astronomers analyze those light curves to learn about the engine, the black hole, the accretion disk, the magnetic fields, the jet itself. After the gamma rays come the afterglow. The jets do not just produce gamma rays, they also produce lower energy radiation, X-rays, ultraviolet, optical, infrared, radio. The afterglow is the longer-lasting emission that follows the initial gamma-ray burst. It can last for days, weeks, sometimes months. The afterglow is produced by the interaction between the jet and the surrounding medium. The jet is plowing through the interstellar gas. The collision heats the gas and produces shock waves. Those shock waves accelerate particles, and those particles emit synchrotron radiation across the entire electromagnetic spectrum. The afterglow is important because it is easier to study than the gamma-ray burst itself. The burst is over in seconds. The afterglow lasts much longer, and it is bright in wavelengths that ground-based telescopes can observe. Optical, infrared, radio. Astronomers can point their telescopes at the location of the burst and watch the afterglow fade over time. They can take spectra, measure the redshift, identify the host galaxy, figure out how far away the burst was, and by studying the afterglow, they can learn about the jet, how fast it was moving, how much energy it carried, how it interacted with the surrounding environment. The Collapsar model predicts that long gamma-ray bursts should be associated with supernovae, specifically a type of supernova called a type IC supernova. Type IC supernovae are core collapse supernovae, where the outer layers of hydrogen and helium have been stripped away before the explosion. What you see is the bare core of the star. Carbon, oxygen, silicon, iron, no hydrogen lines in the spectrum, no helium lines, just the heavy elements. This stripping can happen if the star was in a binary system and the companion star pulled away the outer layers, or it can happen through strong stellar winds. Massive stars shed mass throughout their lives. They blow off their outer layers in powerful winds driven by radiation pressure. By the time the core collapses, the star might have lost most of its hydrogen and helium envelope. What is left is the core, and when that core collapses and produces jets, the explosion you see is a type IC supernova. The Collapsar model predicts that long gamma-ray bursts and type IC supernovae should go hand in hand, and that is exactly what observations have shown. In 2003, astronomers detected a long gamma-ray burst called GRB 030329. A few weeks later, they detected a supernova at the same location, a type IC supernova called SN 2003DH. The timing and location matched perfectly. The burst and the supernova were the same event, the smoking gun. The Collapsar model was correct. Not every long gamma-ray burst is associated with a detectable supernova. Some are too far away. The supernova is there, but it is too faint to see. Others might be genuine failed supernovae, where the collapse produced jets but no explosion. But in the cases where we can see both, the connection is clear. Long gamma-ray bursts are the birth cries of black holes. The jets announcing to the universe that a massive star has died and something new has been born. The energy release of a gamma-ray burst is almost incomprehensible. Let me try to put it in perspective. The sun produces about 4 × 10⁻26 watts of power. That is 4 followed by 26 zeros. Watts are joules per second, so every second the sun puts out 4 × 10⁻26 joules of energy. Over its entire 10 billion year lifetime, the sun will produce about 10 to the 44 joules. A typical long-duration gamma-ray burst releases about 10 to the 44 joules in 10 seconds. The sun's entire life output in 10 seconds. That is the power of a gamma-ray burst. And the most energetic bursts release even more. Some have been measured at 10 to the 47 joules or higher. That is 1,000 times the sun's lifetime output, released in less than a minute. If you could somehow convert mass directly into energy, you would need to annihilate about 3 solar masses to produce that much energy. 3 times the mass of the sun, gone, turned into light, in less than a minute. Gamma-ray bursts do not happen often in any given galaxy. The rate is estimated at about 1 per 100,000 years per galaxy. The Milky Way has about 400 billion stars. Most of them are small. Most of them will never produce a gamma-ray burst. Only the most massive stars, the ones weighing more than about 25 solar masses, have a chance. And even then, the star has to be rotating fast enough to produce jets. If the core collapse does not produce jets, you do not get a gamma-ray burst. You just get a supernova, or a failed supernova. So the rate is low. But the universe is big. There are hundreds of billions of galaxies, and gamma-ray bursts are so bright that we can see them across cosmological distances. The farthest gamma-ray burst ever detected has a redshift of 8.2. The light from that burst has been traveling for more than 13 billion years. We are seeing it as it was when the universe was less than 600 million years old. The burst happened in the early universe, before the Earth existed, before the Sun existed, before the Milky Way had finished assembling itself, and we can still see it. That is how bright gamma-ray bursts are. If a gamma-ray burst went off in our galaxy, close enough and aimed at Earth, it would be catastrophic. The gamma rays would hit the Earth's atmosphere and produce a cascade of secondary particles. Nitrogen and oxygen molecules would be ionized. The ozone layer, which protects us from ultraviolet radiation, would be destroyed. Within weeks, the loss of the ozone layer would allow lethal doses of ultraviolet light to reach the surface. Plants would die. Phytoplankton in the oceans would die. The food chain would collapse. A nearby gamma-ray burst, one within a few thousand light-years aimed directly at Earth, could cause a mass extinction. Some scientists have speculated that past mass extinctions on Earth might have been triggered by gamma-ray bursts. There is no direct evidence for this, but it is possible. The good news is that gamma-ray bursts are rare, and the odds of one going off close enough and aimed directly at Earth are very low. We have not detected any massive stars in our neighborhood that are likely to produce a gamma-ray burst anytime soon. The closest candidate is probably thousands of light-years away. Far enough that even if it went off, the jets would probably miss us. Probably. But the fact that it is even possible, that a single event on the other side of the galaxy could wipe out all life on Earth, is a reminder of how violent the universe can be and how fragile we are. The Collapsar model ties everything together: the collapsing star, the black hole, the accretion disk, the jets, the gamma-ray burst, the hypernova. It is a chain of events that starts with the exhaustion of nuclear fuel and ends with the most violent explosion the universe has to offer. And every step is written into the physics. Nothing is arbitrary. The star runs out of fuel because fusion stops at iron. The core collapses because electron degeneracy pressure cannot hold it up. The black hole forms because the core is too massive for neutron degeneracy pressure to stop the collapse. The jets form because magnetic fields thread through the accretion disk and channel energy outward. The gamma-ray burst happens because the jets are moving at relativistic speeds and the radiation gets beamed forward. The hypernova happens because the jets pump energy into the surrounding star and blow it apart. Every piece fits, and the result is a beacon visible across the entire observable universe. A flash of light announcing that somewhere a massive star has reached the end of its life, collapsed into a black hole, and screamed its death into the void for anyone with eyes to see. The star is gone, not fading, not cooling, not collapsing into a white dwarf or a neutron star that will sit quietly in space for trillions of years, slowly radiating away its heat, gone, obliterated, torn apart by the most violent explosion the universe has to offer. The outer layers, thousands of solar masses of hydrogen and helium and carbon and oxygen and silicon, have been blasted outward at tens of thousands of kilometers per second. The core has vanished behind an event horizon, and what remains, scattered across light years of space, is debris. The ashes of a star that burned so hot and so fast that it ran out of moves in less time than it takes for continents to drift across the surface of a planet. This is the aftermath, the legacy. The cosmic inheritance left behind when a 40 solar mass star reaches the end of its life and screams its death into the void. And that legacy is written in the periodic table. Every atom in your body, heavier than helium, was forged inside a star. Carbon, oxygen, nitrogen, the calcium in your bones, the iron in your blood, the phosphorus in your DNA. None of it existed in the early universe. When the Big Bang happened, the universe made hydrogen and helium and traces of lithium. That was it. Everything else, every element with more than 3 protons in its nucleus, had to be built inside stars. And not just any stars. You need specific kinds of stars, specific processes, specific conditions to make specific elements. The carbon in your body was made inside a red giant during helium fusion. The oxygen came from the same place, built up layer by layer as the star climbed through its fusion stages. The iron came from silicon burning in the final seconds before a core collapse supernova. But iron is not the end of the periodic table. It is only element 26. There are 94 naturally occurring elements. And everything heavier than iron, everything from cobalt and nickel up through gold and platinum and uranium, requires a different process, a process that does not happen in normal stellar fusion. A process that only happens in the most extreme environments the universe can create. Environments like the collapsing core and exploding debris of a hypernova. Hypernova is not an official term, it is jargon, slang. But it is the best word we have for what happens when a star more massive than about 25 solar masses collapses into a black hole and produces jets powerful enough to blow the rest of the star apart. A regular core collapse supernova, the kind that produces a neutron star, releases about 10 to the 51 ergs of energy. Most of that energy comes out as neutrinos. Only about 1%, 10 to the 49 ergs, goes into the kinetic energy of the explosion, the expanding debris. A hypernova releases more, 10 to the 52 ergs, maybe higher, and a much larger fraction of that energy goes into the explosion itself rather than escaping as neutrinos. The result is an explosion that is 10 to 100 times more energetic than a regular supernova. The debris moves faster. The shock waves are stronger, the temperatures are higher, and the nucleosynthesis, the process of building new atomic nuclei, goes into overdrive. Nucleosynthesis during a supernova happens in layers. The inner layers, closest to the core, experience the highest temperatures and densities. Those layers fuse silicon into iron and nickel during the final seconds before collapse. The outer layers, farther from the core, experience lower temperatures. They fuse lighter elements, oxygen, neon, carbon. When the shock wave from the core collapse reaches those layers, it heats them even further. The temperatures spike. And for a brief moment, a few seconds at most, those layers undergo explosive nucleosynthesis. Fusion reactions that would normally take thousands of years happen in an instant. The shock wave compresses the gas, the temperature climbs, and elements that were stable a moment ago suddenly find themselves in an environment hot enough to fuse into something heavier. Oxygen fuses into silicon, silicon fuses into sulfur and calcium. The periodic table gets filled in, element by element, as the shock wave tears through the star, but there is a limit. Fusion stops being energetically favorable at iron. Iron 56 has the highest binding energy per nucleon of any element. Fusing iron into anything heavier costs energy instead of producing it, and fusion reactions, by definition, are exothermic. They release energy. If you have to put energy in, it is not fusion anymore, it is something else. So how do you build elements heavier than iron? You need a different process. A process that does not rely on fusion, and that process is called neutron capture. Neutron capture is exactly what it sounds like. An atomic nucleus captures a neutron. The neutron sticks. The nucleus now has one more neutron than it did before. Its mass number goes up by 1. Its atomic number, the number of protons, stays the same, so the element does not change, not yet, but the isotope does. You have created a heavier version of the same element, and if that heavier isotope is unstable, it will eventually undergo beta decay. One of the neutrons in the nucleus converts into a proton and an electron. The electron gets ejected as a beta particle. The nucleus now has one more proton than it did before. The atomic number goes up by 1. The element changes. You have transmuted one element into another. Capture another neutron, and the process repeats. Capture enough neutrons, let enough beta decays happen, and you can climb the periodic table all the way from iron to uranium and beyond. There are two main types of neutron capture, slow and fast. The slow process, called the S process, happens inside red giant stars over thousands of years. The neutron flux is low. A nucleus captures a neutron, waits around for a while, and if it is unstable, it undergoes beta decay. Then it captures another neutron, then it waits again. The process is slow because there is time between captures for beta decay to happen. The S process builds up elements along the valley of beta stability, the region of the periodic table where isotopes are stable or have long half-lives. It produces about half of the elements heavier than iron. The other half requires something faster, something that does not give nuclei time to beta decay before the next neutron hits. That process is called the R process. The R stands for rapid. The R process happens in environments with an absurdly high neutron flux. so many neutrons flying around that a nucleus gets hit again and again and again before it has time to beta decay. The nucleus captures neutron after neutron, piling them on, becoming more and more neutron-rich, more and more unstable. The captures happen faster than the beta decays. That is the defining characteristic of the R process, rapid neutron capture. The timescale for neutron captures is less than a second. The timescale for beta decay is longer, so the nucleus keeps capturing neutrons, moving farther and farther from the valley of stability into regions of the periodic table where isotopes are so neutron-rich they have never been observed in a laboratory. When the neutron bombardment finally stops, when the environment cools or the neutrons run out, the unstable nuclei start to decay. Beta decay after beta decay, converting neutrons into protons, climbing back towards stability. And when the dust settles, you have elements that the S process cannot make. Elements like gold, platinum, thorium, uranium. Every element heavier than bismuth requires the R process. There is no other way to make them, and the R process only happens in the most extreme environments the universe has to offer. For decades, astronomers debated where the R process happens. You need a high neutron density. You need high temperatures. You need a lot of free neutrons. Core collapse supernovae were the leading candidate. The core collapses, the density spikes, neutrons are everywhere. Surely that is enough. But the models did not quite work. The conditions were close, but not quite right. The neutron flux was high, but maybe not high enough. The E process requires a very specific set of conditions. Too few neutrons, and you do not get rapid capture. Too many, and the nuclei get blown apart by the neutron bombardment before they have a chance to decay. The Goldilocks zone is narrow, and for a long time nobody could prove that core collapse supernovae hit that zone. Then in August 2017, LIGO and Virgo detected gravitational waves from the merger of two neutron stars. Less than 2 seconds later, gamma-ray telescopes detected a short gamma-ray burst from the same location. And over the following days and weeks, optical and infrared telescopes detected a glow, a kilonova, the radioactive decay of freshly synthesized heavy elements produced by the R process in the debris of the neutron star merger. Spectroscopy of the kilonova showed clear signatures of heavy elements, lanthanides, actinides. The R process had happened, right there, in the merger. The debate was over. Neutron star mergers are an R process site, maybe the R process site. The neutron flux is enormous. Two neutron stars colliding releases more free neutrons than almost any other event in the universe. The conditions are perfect, the R process runs wild, and the result is a cloud of freshly minted heavy elements scattered into space, glowing with the light of radioactive decay. But neutron star mergers are rare. They happen maybe once per 100,000 years in a galaxy like the Milky Way. And when they do happen, they produce a lot of heavy elements, but not enough to account for all the gold and platinum and uranium we see in the universe. Something else has to be contributing, and that something else is hypernovae. Specifically, a type of hypernova called a magnetorotational hypernova. The name is a mouthful, but it describes exactly what is happening. The progenitor star is rotating fast. When the core collapses, that rotation speeds up. The magnetic fields, which were already present in the star, get amplified, twisted, compressed, and the combination of rapid rotation and strong magnetic fields drives the jets that power the explosion. Those jets are the key. They create the conditions needed for the R process to happen. Here is how it works. The black hole is feeding. The accretion disk is glowing. The jets are screaming outward at 99% the speed of light. And in the region just outside the black hole, where the accretion disk is hottest and densest, the conditions are perfect for the E process. The density is high, the temperature is high, and there are free neutrons everywhere. Neutrons from the electron capture reactions happening in the collapsing core. Neutrons from the photodisintegration of heavy nuclei in the disk. Neutrons from the decay of neutron-rich isotopes. The neutron flux is so high that nuclei in the disk start capturing them, one after another. Rapid neutron capture, the R process. And within a second, maybe less, those nuclei have climbed all the way up the periodic table, from iron to gold, from nickel to platinum, from lead to uranium. The jets carry this material outward, into the star, through the star, and out into space. When the jets break through the surface of the star and the explosion finally reaches the outer layers, the reprocessed material gets scattered, mixed in with the rest of the debris. The oxygen and carbon and silicon and iron, and all of it, the light elements and the heavy elements, streams outward into the interstellar medium, seeding the galaxy with the raw materials for the next generation of stars and planets. A single magnet or rotational hypernova can produce more than half of all the elements heavier than iron in a localized region of space. Not the entire galaxy, not the entire universe. But in the neighborhood around the explosion, the contribution is enormous. Observations of ancient stars in the Milky Way halo, stars that formed in the early universe, show unusual abundance patterns, high amounts of R process elements, gold, platinum, europium, gadolinium, elements that should not be there in such high concentrations unless something unusual happened nearby. And when astronomers ran models of what kind of explosion could produce those abundance patterns, the answer was clear. A 25 solar mass magnetorotational hypernova, a single event, one star, one explosion, and it was enough to seed an entire region of the early galaxy with heavy elements. The debris from the hypernova expands outward at thousands of kilometers per second. It does not expand uniformly. The jets have punched holes through the star along the poles. Most of the energy went into those jets. The explosion is bipolar. The debris moving along the jet direction is moving faster than the debris moving perpendicular to it. The result is a shape that is not a sphere, more like an hourglass. Or a peanut. The debris in the equatorial regions, far from the jets, is moving slower. Tens of thousands of kilometers per second, still fast by any human standard, but slow compared to the jets. And that debris carries most of the mass, the outer layers of the star, hydrogen and helium that never got close to the core, carbon and oxygen from earlier fusion stages, silicon and sulfur from the final stages, and mixed in with all of that, the A process elements, the gold and platinum and uranium, a few solar masses of iron peak elements from the explosive nuclear synthesis, and traces of everything in between. The debris sweeps through the interstellar medium like a broom. The interstellar medium is not empty, it is thin, a few atoms per cubic centimeter on average, but it is there. Hydrogen, helium, dust grains, molecular clouds. The expanding debris, moving at thousands of kilometers per second, slams into this material and pushes it aside. The collision heats the gas, ionizes it, creates a shock wave that propagates outward ahead of the debris. The shock wave compresses the interstellar gas, and in some cases that compression can trigger the collapse of nearby molecular clouds, the formation of new stars. The hypernova, in its death, becomes the spark that ignites new life. The heavy elements scattered by the explosion, the carbon and oxygen and iron and gold, get incorporated into those new stars and into the planets that form around them, every atom of gold in a wedding ring. every atom of platinum in a catalytic converter, every atom of uranium in a nuclear reactor, all of it came from an exploding star. Most of it came from events like this: hypernovae, neutron star mergers, the violent deaths of massive objects in the most extreme environments the universe can create. The black hole left behind by the hypernova does not just sit there quietly, it is spinning fast. Close to the maximum rotation rate allowed by general relativity, the spin distorts spacetime around the black hole. The ergosphere, the region outside the event horizon where spacetime is dragged around by the black hole's rotation, extends outward for several times the radius of the horizon. Any object entering the ergosphere is forced to move in the direction of the black hole's spin. You cannot stand still. Spacetime itself is moving, and that motion carries energy that can, in principle, be extracted. The Penrose process, named after Roger Penrose, who first described it, allows you to extract rotational energy from a spinning black hole by dropping material into the ergosphere and using the dragged spacetime to accelerate it back out. The material leaves with more energy than it came in with. The extra energy comes from the black hole's rotation. The black hole spins down slightly, and the material speeds up. This process might be responsible for some of the energy in the jets. It is hard to say for sure. The details depend on the magnetic field structure and the accretion rate and a dozen other variables, but the principle is sound. Spinning black holes are energy reservoirs, and given the right conditions, that energy can be tapped. The gravitational influence of the black hole extends far beyond the event horizon. Gravity is a long-range force. It does not care about surfaces or boundaries, it just pulls. An object orbiting the black hole at a distance of a few hundred kilometers experiences a gravitational pull comparable to what the Earth experiences from the Sun. Except the source of that pull is not a glowing ball of gas 1,000,000 kilometers across. It is a region of space-time 4 to 6 kilometers across, where the curvature has become so extreme that not even light can escape. The black hole does not glow. It does not emit light, but its gravity shapes the orbits of everything around it. Gas, dust, stars. If another star wanders too close, the black hole can capture it, tear it apart, feed on the debris. And if the black hole is part of a binary system orbiting another massive star, the two objects will eventually spiral into each other and merge. The merger will produce gravitational waves, ripples in spacetime itself, propagating outward at the speed of light, carrying information about the masses and spins of the objects that merged. LIGO and Virgo and other gravitational wave observatories are detecting these mergers, not from hypernovae directly, but from the black holes left behind by hypernovae, the remnants of these violent deaths, orbiting each other, spiraling inward, merging in a final burst of gravitational radiation. The imprint of the hypernova on the galaxy is profound. The energy released by the explosion, 10 to the 52 ergs or more, heats the surrounding interstellar medium, creates bubbles of hot gas, drives winds that can blow material out of the galaxy entirely. The heavy elements scattered by the explosion enrich the interstellar medium with the raw materials needed to form planets, rocky planets, terrestrial planets, planets like Earth. Without the process, without the gold and platinum and uranium produced in hypernovae and neutron star mergers, the universe would be a different place. There would be no heavy elements beyond the SAR process contributions from red giants, no thorium, no uranium, no radioactive isotopes to heat planetary interiors and drive plate tectonics, no gold or platinum to conduct electricity or resist corrosion. The periodic table would stop at lead, maybe bismuth. Everything beyond that would not exist. And the Earth, if it formed at all, would be a different kind of world, colder, geologically dead. Without the radioactive decay of uranium and thorium in the mantle, there would be no heat to drive convection. No convection means no plate tectonics, no magnetic field, no atmosphere. The planet would be a frozen ball of rock, unable to hold on to water or air or life. Hypernovae are rare, rarer than regular core collapse supernovae. The progenitor star has to be massive, more than 25 solar masses. It has to be rotating rapidly, and it has to have the right magnetic field structure. If any of those conditions are not met, the collapse might still produce a black hole, but it will not produce jets. Without jets, there is no hypernova, just a failed supernova, or a regular supernova that produces a neutron star instead. The rate of hypernovae in a galaxy like the Milky Way is estimated at about 1 per million years, maybe less. Over the 13 billion year history of the galaxy, that adds up to maybe 10,000 events. Not many, but enough, because each event produces so much. Enough heavy elements to enrich entire molecular clouds, enough energy to shape the structure of the interstellar medium, enough gravitational waves and electromagnetic radiation to be detected across the universe. Hypernovae are rare, but their impact is enormous. The debris from the hypernova continues to expand. Thousands of years after the explosion, the shock wave has traveled dozens of light years. The debris has mixed with the interstellar medium. The heavy elements have been incorporated into new molecular clouds. And somewhere in one of those clouds, a new star is forming. A star that will contain the atoms forged in the hypernova: carbon, oxygen, iron, gold, uranium. The atoms cycle through the galaxy, from stars to space, from space to new stars, each generation slightly richer in heavy elements than the last. The Sun is a third-generation star, maybe fourth. It formed from a cloud that already contained carbon and oxygen and iron, elements that came from earlier generations of stars that lived and died and scattered their ashes into space. And when the Sun formed, it brought with it a disk of gas and dust. That disk condensed into planets, rocky planets, gas giants, asteroids, comets, and one of those rocky planets, sitting in the habitable zone at just the right distance from the Sun, developed an atmosphere, oceans, plate tectonics, and eventually life. Every atom in your body is recycled stardust, but not just any stardust. The carbon and oxygen came from red giants. The iron came from supernovae, and the gold, the trace amounts of gold in your body, a few milligrams scattered across your cells, came from events like this: hypernovae, neutron star mergers, the violent deaths of massive objects in the most extreme conditions the universe can produce. You are made of stellar ashes, and some of those ashes were forged in the most violent explosion the universe has to offer. The black hole remains, long after the debris has dispersed, long after the shock wave has faded, long after the gamma-ray burst has been redshifted into invisibility by the expansion of the universe. The black hole sits there, spinning, a permanent scar in space-time, a reminder that something massive lived and died here. And that death, that violent, catastrophic, obliterating death, was not the end. It was a transformation. The star is gone, but its legacy endures, in the heavy elements scattered across the galaxy, in the new stars forming from enriched molecular clouds, in the planets orbiting those stars, in the life that might one day arise on those planets. The hypernova destroyed a star, but it also created the future. And if you want to understand where you came from, if you want to know why the universe looks the way it does, why the Earth has the elements it has, why life exists at all, you have to look back at events like this. the death of a 40 solar mass star, the birth of a black hole, the scream of relativistic jets tearing across space at 99% the speed of light, the flash of a gamma-ray burst visible across the universe. That flash carries a message. It says a star has died here, and in dying, it has given the universe a gift, the elements needed to build worlds, the raw materials needed for life, the atoms needed to make you. The hypernova is gone, but its echoes remain, and those echoes are everywhere, in every atom heavier than iron, in every planet with a molten core, in every living thing that has ever existed. The hypernova is not just an explosion, it is an act of creation, and the universe is better for it. The explosion is over, the jets have shut off, the gamma-ray burst, that blinding flash of the highest energy light in the electromagnetic spectrum, has faded. The debris from the hypernova is streaming outward into space at thousands of kilometers per second, carrying with it the heavy elements forged in the final seconds of a massive star's life. And the black hole, the newborn singularity wrapped in an event horizon, sits at the center of it all, spinning, invisible, a permanent scar in the fabric of space-time. The whole event, from the moment the core began to collapse to the moment the jets broke through the surface of the star and the gamma-ray burst lit up the sky, took less than a minute, maybe 10 seconds, maybe 30. A single fleeting moment in the life of the universe, and then it was gone. But the light from that moment is still traveling. The gamma rays that erupted from the jets when they broke through the star are racing outward at the speed of light. And if you are sitting in the right place, at the right time, with the right instruments pointed in the right direction, you can catch them, you can see the explosion. Not as it is happening now, because by the time the light reaches you, the event is over, long over. But as it happened then, millions of years ago, billions of years ago, the light is a messenger, a recording, a snapshot of a moment when a star died and a black hole was born. And humanity has spent the last 60 years learning how to read that message. The problem is that gamma-ray bursts do not warn you before they happen. They do not send out a press release. They do not schedule themselves on a calendar. They just go off, randomly, without warning. Somewhere in the universe, a massive star collapses, a black hole forms, jets erupt. A gamma-ray burst screams across the cosmos. And if your telescope happens to be looking at that patch of sky at that exact moment, you see it. If your telescope is pointed somewhere else, you miss it. And because gamma-ray bursts are short, because they last anywhere from a fraction of a second to a few minutes at most, you do not get a second chance. Blink and it is gone. Point your telescope at the wrong part of the sky and you see nothing. The burst happens. The universe moves on, and you are left wondering what you missed. That is the challenge. How do you observe something that happens randomly, lasts for seconds, and occurs at distances measured in billions of light years? How do you catch lightning in a bottle when you do not know when or where the lightning is going to strike? The answer, it turns out, is satellites. Lots of satellites, watching the entire sky, all the time, waiting. The first gamma-ray bursts were detected by accident. July 1967, the Vela satellites, a constellation of spacecraft launched by the United States military, picked up a strange signal, a flash of gamma rays, not from Earth, not from the Sun, from somewhere out in space. The Vela satellites were not designed to study astronomy. They were designed to detect nuclear weapons tests. Specifically, covert nuclear weapons tests by the Soviet Union. The Partial Nuclear Test Ban Treaty, signed in 1963, prohibited testing nuclear weapons in the atmosphere, in space or underwater. but nobody trusted the Soviets to follow the rules. So the military launched Vela to watch, to listen, to catch them in the act if they tried anything. Vela worked. It detected gamma rays. But they were not coming from Soviet nuclear tests. They were coming from space, deep space, and they did not look like anything a bomb would produce. The signals were too short, too energetic, and they were coming from random directions. No clustering near the Moon or Earth or anywhere the Soviets could plausibly hide a weapon, just random points in the sky. The military sat on the data for 6 years, classified. It was not until 1973 that a team of scientists from Los Alamos National Laboratory, led by Ray Klebersadil, published a paper describing 16 gamma-ray events detected between 1969 and 1972. They called them gamma-ray bursts. And the astronomical community collectively scratched its head because nobody had any idea what was causing them. The distance question haunted the field for decades. Were the bursts coming from nearby objects in the Milky Way, or were they cosmological, billions of light-years away? If they were nearby, the energy budget was manageable, a few times 10 to the 39 ergs, bright but not impossible. If they were cosmological, the energy budget exploded, 10 to the 51 ergs, maybe more. That is more energy than most galaxies produce in a year, and it all has to come out in 10 seconds. The idea seemed absurd, but the alternative, that the bursts were coming from nearby sources, did not fit the data either. The Compton Gamma Ray Observatory, launched in 1991, detected thousands of gamma-ray bursts over the course of its 9-year mission, and those bursts were distributed uniformly across the sky. No clustering, no preference for the galactic plane. That meant they could not be coming from objects in the Milky Way. They had to be cosmological, outside the galaxy, billions of light-years away. The breakthrough came in 1997, February 28th. The Beppo Sachs satellite, an Italian-Dutch mission, detected a gamma-ray burst and for the first time managed to pinpoint its location accurately enough that ground-based telescopes could follow up. Within hours, optical telescopes were pointed at the location and they saw something, a fading glow, an afterglow. The burst itself was over, but the light it left behind was still there, dimming slowly over the course of days and weeks. Spectroscopy of the afterglow revealed the redshift, 0.835. That put the burst at a distance of roughly 6 billion light-years. The debate was over. Gamma-ray bursts were cosmological, and the energy budget was real, 10 to the 51 ergs, released in less than a minute. That discovery changed everything, because if gamma-ray bursts were that far away and that energetic, they had to be coming from something extraordinary, something cataclysmic. The leading candidates were collapsing massive stars and merging neutron stars, and the way to tell the difference was to look at the duration. Short gamma-ray bursts, the ones lasting less than 2 seconds, were likely coming from neutron star mergers. Long gamma-ray bursts, the ones lasting more than 2 seconds, were likely coming from collapsing stars. The Collapsar model, the Hypernova, the relativistic jets punching through the star and screaming out into space at 99% the speed of light. But detecting the burst is only the first step. Gamma rays do not tell you much by themselves. They tell you something exploded. They tell you roughly how much energy was involved, but they do not tell you what exploded or how far away it was or what the surrounding environment looked like. For that, you need the afterglow. And the afterglow is not made of gamma rays. It is made of X-rays and optical light and infrared and radio waves. Lower energy radiation produced by the interaction between the jet and the surrounding medium. The jet plows through the interstellar gas. The collision heats the gas and produces shock waves, and those shockwaves emit synchrotron radiation across the entire electromagnetic spectrum. The afterglow fades over time, hours, days, weeks, but while it is still bright, you can study it, you can take spectra, you can measure the redshift, you can identify the host galaxy, you can figure out what kind of star produced the burst and what kind of environment it lived in. The problem is time. The afterglow starts fading the moment the burst goes off. If you want to catch it while it is still bright, you have to move fast, and by fast I mean within minutes, ideally within seconds. You need to detect the gamma-ray burst, calculate its position, send an alert to ground-based telescopes, slew those telescopes to the right coordinates, and start taking data. All of that has to happen faster than the afterglow fades, and the afterglow does not wait for you. It fades whether you are ready or not. That is why NASA launched SWIFT in November 2004. SWIFT is a satellite designed specifically to detect gamma-ray bursts and respond to them as quickly as possible. The name is descriptive. It is fast. When SWIFT's gamma-ray detectors pick up a burst, the satellite calculates the position automatically, slews its X-ray and optical telescopes to that position, and starts observing the afterglow. The entire process takes less than a minute, often less than 30 seconds, and while SWIFT is observing, it sends out an alert to telescopes all over the world, ground-based observatories, other satellites, radio telescopes, infrared telescopes. Everybody gets the coordinates, everybody points. And within minutes, dozens of telescopes are watching the same patch of sky, capturing the afterglow at every wavelength from radio to gamma rays. The coordination is remarkable. SWIFT detects the burst. Within seconds, an automated alert goes out to a network called the Gamma Ray Burst Coordinates Network. The network distributes the coordinates to hundreds of observatories around the world. Automated systems at those observatories receive the alert and slew their telescopes to the target. Human astronomers, alerted by email or text message, wake up in the middle of the night and start taking data. And all of this happens while the afterglow is still bright, while there is still something to see. The window is narrow. Miss it and you miss the burst. Catch it and you get a front row seat to the most violent explosion in the universe. The Fermi Gamma Ray Space Telescope, launched in June 2008, added another layer. Fermi carries two main instruments: the Gamma Ray Burst Monitor, which watches the entire sky for bursts, and the Large Area Telescope, which observes the highest energy gamma rays. Between them, Fermi detects about 240 gamma-ray bursts per year. Not all of them are long-duration bursts from collapsing stars. Some are short bursts from neutron star mergers, but the long ones, the ones tied to the Collapsar model, those are the ones that tell us about black hole formation, about jets, about the death of massive stars, and every burst Fermi detects gets added to the catalogue. The coordinates get distributed, the follow-up observations begin, and slowly, burst by burst, observation by observation, the picture comes into focus. The importance of rapid alerts cannot be overstated. When a gamma-ray burst goes off, the clock starts ticking immediately. The gamma rays arrive first. They travel at the speed of light. Nothing is faster. The X-ray afterglow follows within seconds, the optical afterglow within minutes, the infrared afterglow within hours, and the radio afterglow, the longest-lasting component, can persist for weeks or months. But the brightness drops with time. The faster you observe, the more light you collect, the more data you get. Wait too long, and the afterglow dims below detectability. You are left with nothing. Just a faint smudge on an image that could be anything: a distant galaxy, a faint star. Background noise. Without the early observations, without the rapid response, you lose the ability to study the burst in detail. You lose the redshift, you lose the host galaxy, you lose the context. Multi-messenger astronomy has added a new dimension. Gamma-ray bursts are not the only signal produced by collapsing stars and merging compact objects. They also produce neutrinos. And in the case of merging neutron stars or black holes, they produce gravitational waves. Neutrinos are nearly massless particles that barely interact with matter. A neutrino can pass through the entire Earth without hitting a single atom. They are produced in enormous numbers during core collapse supernovae and hypernovae. Billions of neutrinos streaming out from the collapsing core, carrying energy away, leaving the star behind. Most of those neutrinos escape into space and are never detected, but a tiny fraction of them pass through detectors on Earth. Neutrino observatories like IceCube, a cubic kilometer detector buried in the ice at the South Pole, can catch them. When a nearby supernova goes off, IceCube will see a burst of neutrinos, not just a few, dozens, maybe hundreds. Enough to pinpoint the direction and confirm that a core collapse has happened. Gravitational waves are ripples in space-time itself. When two massive objects, like neutron stars or black holes, spiral into each other and merge, they release energy in the form of gravitational waves. Those waves propagate outward at the speed of light, stretching and compressing space-time as they pass. LIGO and Virgo, the gravitational wave observatories, have been detecting these waves since 2015. The first confirmed detection was a merger of two black holes. The signal was unmistakable, a chirp in the data, rising in frequency as the black holes spiraled inward, then cutting off abruptly as they merged. Since then, LIGO and Virgo have detected dozens of mergers, black hole mergers, neutron star mergers, and in August 2017 they detected a neutron star merger and saw the gamma-ray burst that went with it, a short burst, less than 2 seconds, detected by Fermi less than 2 seconds after the gravitational wave signal. It was the first time humanity had observed the same event in both gravitational waves and electromagnetic radiation. Multi-messenger astronomy. Two independent signals from the same source. And the story they told was consistent. Neutron stars merged. A gamma-ray burst erupted. A kilonova glowed. The heavy elements scattered into space. Everything fit. For hypernovae, the multi-messenger picture is still incomplete. We have not detected neutrinos from a hypernova yet. The last nearby supernova visible to the naked eye was supernova 1987A, which went off in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 160,000 light-years away. That supernova produced a burst of neutrinos detected by 3 separate neutrino observatories, 25 neutrinos total. Not many, but enough to confirm that the core had collapsed. Supernova 1987A was not a hypernova. It was a regular core collapse supernova that left behind a neutron star. But the neutrino detection proved that neutrinos from core collapses could be detected. If a hypernova goes off in the Milky Way or a nearby galaxy, neutrino detectors will see it, and the neutrinos will arrive before the light, before the gamma rays. Because neutrinos do not interact with matter, they do not get slowed down by the overlying layers of the star. They just stream out, straight through everything, at the speed of light. If a hypernova happens close enough, neutrino detectors will get the first alert. A burst of neutrinos. Seconds before the gamma rays arrive, seconds before the optical light. That early warning would be invaluable. It would give astronomers time to point their telescopes, to get ready, to capture the burst from the very beginning. Gravitational waves from a single collapsing star are harder to detect. LIGO and Virgo are sensitive to the frequencies produced by merging compact objects. Black holes and neutron stars orbiting each other, spiraling inward, colliding. Those events produce gravitational waves at frequencies between 10 Hz and a few kilohertz. LIGO and Virgo can detect those waves from hundreds of millions of light-years away, but a single collapsing stellar core produces gravitational waves at higher frequencies, and the amplitude is smaller. The signal is weaker. LIGO might be able to detect a nearby hypernova, one within the Milky Way or a nearby galaxy, but anything farther than that is probably below the detection threshold. Future detectors, like the Einstein telescope or Cosmic Explorer, will be more sensitive. They will be able to see farther. Detect weaker signals. If a hypernova goes off anywhere in the local universe, those detectors will see the gravitational waves. And when they do, we will have another piece of the puzzle, another way to study the collapse, another messenger carrying information from the heart of the explosion. The data from all these observations feed back into the models. Every gamma-ray burst we detect, every afterglow we study, every redshift we measure, every host galaxy we identify, every spectrum we analyze. All of it goes into refining our understanding of what is happening. The Collapsar model is not just a theory, it is a framework, a way of organizing the observations, and every new observation either confirms the model or forces us to revise it. Most of the time, the observations confirm the model. The gamma-ray bursts we see match the predictions. The durations are right, the energies are right. The association with Type IC supernovae is clear. The host galaxies are young, star-forming galaxies where massive stars are being born and dying. Everything fits, but not always. There are outliers, bursts that do not quite fit the pattern. Short bursts that seem to come from old galaxies where all the massive stars should have died billions of years ago. Long bursts that do not have an associated supernova. Bursts that are too bright or too faint or too long or too short. Every outlier is a clue, a hint that there is more going on than we understand. Maybe there are multiple pathways to producing a gamma-ray burst. Maybe the Collapsar model is not the only game in town. Maybe some bursts are coming from something we have not thought of yet. A new kind of event, a new kind of object. The universe has a way of surprising us. Every time we think we have it figured out, it shows us something we did not expect. And the only way to find those surprises is to keep looking, keep observing. Keep detecting bursts and studying afterglows and measuring redshifts and building up the catalogue of events until the patterns emerge. The localization challenge is real. Gamma rays do not focus the way optical light does. You cannot build a gamma-ray telescope with a mirror that concentrates the light into a sharp image. Gamma rays are too energetic. They pass through most materials. The ones that do interact get absorbed, not reflected. So gamma-ray detectors work differently. They detect the direction a gamma-ray came from by measuring where it hit the detector and what angle it entered at. But the precision is limited. A gamma-ray burst detected by a single satellite can only be localized to within a few arc-minutes. That is a circle on the sky roughly the size of the full moon. Within that circle, there could be dozens or hundreds of galaxies. You cannot tell which one hosted the burst. You cannot identify the progenitor star. You need better localization, and you get that by detecting the afterglow. X-ray afterglows can be localized to within a few arc-seconds. Optical afterglows to within a fraction of an arc-second. That is precise enough to pinpoint the host galaxy. To identify the exact region where the star was before it exploded, to see if there are other young massive stars nearby, to measure the metallicity of the gas in that region, and figure out what kind of environment the progenitor star formed in. The technological progress over the last 30 years has been extraordinary. In the 1990s, detecting a gamma-ray burst meant waiting for a satellite to downlink its data to Earth, manually analyzing the data to figure out where the burst came from, and then calling up an observatory and asking them to point their telescope at the coordinates. By the time you did all that, hours had passed. The afterglow had faded. You missed it. Now, the entire process is automated. The satellite detects the burst. The coordinates are calculated on board. The alert is transmitted within seconds. Automated systems at observatories around the world receive the alert and start observing within minutes. The entire chain, from burst to observation, happens faster than a human could react. And the data quality has improved too. Modern telescopes can detect afterglows that are 1,000 times fainter than what was possible in the 1990s. Spectroscopy that used to take hours now takes minutes. Multi-wavelength observations, coordinating optical and infrared and radio telescopes, happen routinely. We are not just detecting gamma-ray bursts anymore. We are studying them in detail, with precision. The orbiting observatories are only part of the story. Ground-based telescopes play a crucial role. Optical and infrared telescopes can study the afterglow in detail, take spectra, measure chemical abundances, identify the elements present in the debris. Radio telescopes can observe the afterglow weeks or months after the burst, long after the optical light has faded. Radio emission from the jet persists for a long time because the jet is still plowing through the interstellar medium, still driving shock waves, still accelerating particles. By watching how the radio afterglow evolves over time, astronomers can measure the density of the surrounding medium, the energy of the jet, the speed of the ejector. All of that feeds into the models. All of it helps refine our understanding of what happened. And then there are the host galaxies. Every gamma-ray burst happens somewhere, inside a galaxy, near a star-forming region, in a molecular cloud. By studying the host galaxy, astronomers can learn about the environment where the progenitor star formed. Young galaxies, the ones actively forming stars, have high metallicity gas in their star-forming regions. Low metallicity galaxies, the ones that have not had much time to enrich their gas with heavy elements, produce stars with different properties: lower mass, lower metallicity, different rotation rates. All of that affects whether the star will produce a gamma-ray burst when it dies. High metallicity stars tend to lose mass through stellar winds. By the time the core collapses, they have shed so much of their outer layers that there is not enough material left to produce a long-duration burst. Low metallicity stars hold on to their mass. They retain their hydrogen and helium envelopes. And when the core collapses, the jets have to punch through all that material. The burst lasts longer. The energy is higher. By studying the host galaxies, astronomers can test these predictions, see if the observed burst properties match what the models say should happen. The coordination between space-based and ground-based observations has become seamless. Satellites like SWIFT and Fermi and the recently launched SVOM detect the bursts. They calculate the coordinates. They send out alerts. Ground-based telescopes receive the alerts and start observing. Optical telescopes capture the early afterglow. Infrared telescopes watch as the light fades. Radio telescopes monitor the late-time emission. Spectroscopy measures the redshift and chemical composition. And all of that data, from every telescope, from every wavelength, gets combined into a coherent picture. A single event observed from every possible angle. That is how we study gamma-ray bursts now. That is how we learn what they are and where they come from and what they tell us about the universe. The observations validate the physics. Every gamma-ray burst we study confirms that the Collapsar model is on the right track. The jets are real. The black holes are real. The connection between long gamma-ray bursts and type IC supernovae is real. The energy budget works out. The timescales match. The light curves fit the predictions. There are still details to work out, still questions to answer, but the broad picture is clear. Massive stars collapse. Black holes form. Jets erupt. Gamma-ray bursts light up the sky. And we, sitting on a small rocky planet orbiting an average star in an average galaxy, can watch it happen. We can catch the light from those explosions and study it and learn from it. We can see across billions of light years and billions of years of cosmic history. We can watch stars die and black holes form. And every observation, every burst, every afterglow brings us one step closer to understanding the most violent events in the universe. The explosions are over. The stars are gone, but their light is still traveling, still carrying the message, and we are learning how to read it. One burst at a time, one observation at a time, one piece of data at a time. The universe is violent, but it is also generous. It shows us its secrets if we know where to look. And humanity has learnt to look. We have built the instruments, we have launched the satellites, we have trained the telescopes on the sky, and we are watching, waiting, ready for the next burst, the next explosion. The next moment when a star dies and a black hole is born and the universe lights up with the scream of collapsing matter and erupting jets and gamma rays screaming across the cosmos at the speed of light. The next chapter is already written. It is written in the stars, in the massive ones still burning, in the ones on the edge of collapse, in the ones whose cores are filling with iron even now, building toward the moment when fusion stops and gravity wins and the collapse begins. Those stars are out there, right now, and when they go, we will be watching. Violence built you, not metaphorically, not poetically, literally. Every atom in your body, heavier than helium, was forged inside a dying star. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, the zinc in your cells, the copper threading through your nerves. None of it existed when the universe began. All of it had to be built, atom by atom, element by element. Inside the cores of massive stars that lived fast, burned bright, and died screaming. And when those stars exploded, when they tore themselves apart in the most violent events the cosmos can produce, they scattered those atoms into space, into clouds of gas and dust that eventually collapsed under their own gravity to form new stars, new planets, new worlds. One of those worlds became Earth. And some of those atoms became you. You are made of star corpses, and the most violent star deaths, the hypernovae, the ones that produce black holes and relativistic jets and gamma-ray bursts, those are the ones that gave you some of the rarest and most essential elements you are made of. The zinc that keeps your immune system running, the iodine in your thyroid, the trace elements scattered through your tissues that you would die without. They came from hypernovae, from explosions so energetic they outshone entire galaxies, from jets moving at 99% the speed of light, from the collapse of stellar cores into black holes. Violence built you, and violence is still building the universe. That is the paradox at the heart of cosmic evolution. The most destructive events in nature are also the most creative. A hypernova destroys a star, obliterates it, tears it apart, and scatters its guts across light years of space. But in doing so, it creates. It forges elements that did not exist before. It enriches the interstellar medium with the raw materials needed to build planets. It triggers the collapse of nearby molecular clouds, sparking the formation of new stars. It injects energy into the galaxy, driving winds that shape the structure of the gas and dust, carving out bubbles and shells that will eventually become the nurseries for the next generation of stars. Destruction and creation are not opposites. They are two sides of the same process. You cannot have one without the other. The universe does not build gently. It builds violently. And the violence is not a bug. It is a feature. Consider the black hole left behind. For decades, black holes were treated as endpoints, dead things, cosmic graves where matter goes to disappear forever. And, in a sense, that is true. Once something crosses the event horizon, it is gone from the universe, cut off, inaccessible. The information about what it was, what it contained, how it was structured, all of that is lost, hidden behind a wall in space-time that nothing can ever cross outward. But black holes are not passive. They are not inert. They shape the space around them. They warp the fabric of the universe. And they power some of the most energetic phenomena we have ever observed. The jets from a hypernova are powered by the black hole. The accretion disk glowing around it is fed by the black hole's gravity. The energy released during the explosion, the 10 to the 52 ergs or more that blow the star apart, much of that energy comes from matter falling into the black hole. The black hole is not an endpoint, it is an engine, a dynamo, a mechanism for converting mass into energy with an efficiency that makes fusion look wasteful. And black holes do not just sit there after the explosion is over, they grow. If the black hole is part of a binary system, if it is orbiting another massive star, it can pull material off that star, strip away its outer layers, feed on them. The accretion process starts again. A new disk forms. New jets might erupt. The black hole gets heavier, and if the companion star is massive enough, it will eventually collapse too. Another core collapse, another black hole, and the two black holes will orbit each other, spiraling inward over millions or billions of years until they merge. The merger releases gravitational waves, ripples in space-time that carry energy away from the system at the speed of light. LIGO and Virgo have detected dozens of these mergers, each one a confirmation that black holes are not static. They are dynamic. They interact, they evolve. They are integral components of the galactic ecosystem, shaping the structure of galaxies, regulating star formation, redistributing energy and mass across scales that span from individual stars to galaxy clusters. There is something almost architectural about it. The universe is not random, it is structured. Galaxies have shapes, spirals, ellipticals, irregulars. Those shapes are not accidents. They are the result of processes that have been running for billions of years. Star formation, supernova feedback, black hole accretion, gas inflows, gas outflows. Mergers. Every galaxy is a battleground where gravity is trying to pull everything together and energy is trying to blow everything apart. And black holes, the ones sitting at the centers of galaxies and the ones scattered through the galactic disk, are key players in that battle. Supermassive black holes at galactic centers, the ones weighing millions or billions of solar masses, can regulate star formation across an entire galaxy. When they feed, when gas falls into the accretion disk and heats up and produces jets, those jets can blow gas out of the galaxy entirely, shut down star formation, turn a spiral galaxy into a dead elliptical. And stellar mass black holes, the ones left behind by hypernovae, contribute to the same process on smaller scales. They inject energy into the interstellar medium, They stir the gas, they trigger turbulence that can either enhance star formation or suppress it, depending on the conditions. Black holes are not passive remnants. They are architects, sculptors, forces that shape the universe at every scale. The elements forged in hypernovae carry that legacy forward. Take gold. Every atom of gold on Earth, every fleck of gold in a wedding ring, every ounce of gold in a vault somewhere came from an R-process event, either a hypernova or a neutron star merger. Gold is not made in regular stars. It cannot be. The R-process requires a neutron flux so high that nuclei get bombarded with neutrons faster than they can beta decay. That only happens in the most extreme environments. The accretion disk around a newborn black hole, the debris from a neutron star merger. Those are the only places in the universe where gold gets made, and once it is made, it gets scattered, mixed into the interstellar medium, incorporated into new molecular clouds, and eventually, billions of years later, it ends up in a planet, in a crust, in a vein of ore that some human digs up and melts down and shapes into a ring. The gold in that ring is older than the Earth, older than the Sun. It was forged in an explosion that happened billions of years ago in a part of the galaxy that no longer exists in any recognizable form. The star is gone. The black hole might still be out there somewhere, drifting through space, invisible, but the gold remains, a permanent record of the violence that created it, or zinc. Zinc is one of the most important trace elements in the human body. You need it for your immune system, for wound healing, for DNA synthesis, for taste and smell. A severe zinc deficiency will kill you, and zinc, like gold, is made in hypernovae. Specifically, it is made in the Re process, the rapid neutron capture that happens in the accretion disk or the debris stream around a newly formed black hole. In 2021, astronomers found a star called SMSSJ 200322, 54,114,203. 3. The name is a mouthful. Nobody calls it that. They call it the hypernova star, because it formed about 13 billion years ago, less than a billion years after the Big Bang, from a cloud of gas that had been enriched by a single hypernova. One explosion, one star, and the chemical fingerprint of that explosion is written into the hypernova star's spectrum. Low iron, high zinc, high europium, high thorium, all of them reprocess elements, all of them traceable back to a single magnet or rotational hypernova that went off in the early universe and seeded a region of space with the heavy elements needed to build planets, to build life. The hypernova star is still there, still glowing, about 7,500 light-years from the Sun. You could point a telescope at it tonight and see the light from a star that remembers the violence that built it. The cycle does not stop. New stars are forming right now, in the Milky Way, in every galaxy across the universe. Molecular clouds are collapsing, protostars are igniting, main sequence stars are burning hydrogen, red giants are fusing helium. Massive stars are climbing through their fusion stages, building heavier and heavier elements in their cores, racing toward the moment when they run out of fuel and the collapse begins. Some of those stars will produce hypernovae, some will produce regular supernovae. Some will collapse quietly into black holes without exploding at all. And every one of those events will contribute to the ongoing enrichment of the interstellar medium. More carbon, more oxygen, more iron, more zinc, more gold, more uranium. The periodic table is being filled in, one explosion at a time, one generation of stars at a time. And the process has been running for 13 billion years. It will keep running for trillions more. As long as there are stars, As long as there is gas to form new stars, the cycle continues. Birth, life, death, rebirth. The universe is not winding down, it is building, slowly, violently, relentlessly, and the building blocks are forged in fire. There is a poetic symmetry to the fact that the most violent deaths produce the seeds of new life. A star collapses, a black hole forms, jets erupt, the star explodes. The debris scatters, and somewhere in that debris, mixed in with the hydrogen and helium that were there from the beginning, are atoms of carbon and nitrogen and oxygen and iron and zinc and gold and uranium, atoms that did not exist before, atoms that were built in the final seconds of the star's life, and those atoms drift through space for millions of years, cooling, mixing with other clouds, condensing into denser regions. Eventually, gravity takes over again, the cloud collapses, a new star forms, and around that star, a disk of gas and dust. That disk contains the atoms from the hypernova, the heavy elements, and over millions of years, that disk condenses into planets, rocky planets, worlds with solid surfaces and molten cores and atmospheres. One of those planets might be in the habitable zone, the right distance from the star, not too hot, not too cold. Water can exist as a liquid, and if the conditions are right, if the planet has the right chemistry and the right energy sources and enough time, life might emerge. Single-celled organisms at first, then multicellular, then complex, then intelligent. And those organisms, whatever form they take, will be made of the atoms scattered by hypernovae billions of years earlier. The violence that destroyed a star will have created the conditions for life. That is not a metaphor. That is the history of the universe. That is your history. The mysteries are not solved, not by a long shot. We understand the broad picture. Massive stars collapse, black holes form, jets erupt. Hypernovae scatter heavy elements. The cycle continues, but the details are still murky. We do not know exactly what triggers the jets. We know magnetic fields are involved. We know rotation matters. But the exact mechanism, the precise sequence of events that takes a collapsing core and turns it into a pair of relativistic jets screaming outward at 99% the speed of light, that is still an active area of research. Simulations help. Supercomputers running magnetohydrodynamic codes can model the collapse in detail, but the physics is complicated. The equations are nonlinear. Small changes in the initial conditions can produce wildly different outcomes. One simulation produces jets, another produces a failed supernova where the jets never launch and the star just collapses into a black hole. The difference between the two scenarios can come down to the exact strength of the magnetic field or the exact rotation rate of the core. And we cannot measure those quantities in real stars before they collapse. We have to wait for them to explode and then work backward from the observations. Gamma-ray bursts are another mystery. We know long-duration gamma-ray bursts come from collapsing massive stars. We know the Collapsar model works, but we do not know why some collapsing stars produce gamma-ray bursts and others do not. The leading idea is that it comes down to rotation. A star has to be rotating fast enough to produce jets. If the rotation is too slow, the collapse produces a black hole, but no jets, no gamma-ray burst, just a failed supernova. But how fast is fast enough? And how common are rapidly rotating massive stars? Those are open questions. Observations suggest that most massive stars are not rotating fast enough to produce gamma-ray bursts when they collapse. Maybe only 1 in 100, maybe 1 in 1,000. The exact fraction depends on metallicity and binary interactions and a dozen other factors. And then there is the beaming. The jets are narrow. If the jet is not pointing toward Earth, we do not see the gamma-ray burst. We see a faint supernova instead, or nothing at all. So the true rate of hypernovae in the universe might be much higher than the observed rate of gamma-ray bursts. We are only seeing the ones aimed at us. The rest go off unnoticed. Their light and energy streaming across the cosmos in directions we never look. Black hole formation itself is still not fully understood. We know that if the core is heavy enough, if it weighs more than about 2 solar masses, neutron degeneracy pressure cannot hold it up. The core collapses into a black hole, but the exact mass threshold is uncertain. It depends on the equation of state. The relationship between pressure and density at nuclear densities, and nobody knows what that relationship is, not precisely. The strong nuclear force, which holds protons and neutrons together inside atomic nuclei, starts to play a role at those densities, and the strong force is complicated. It is not well understood at the extreme pressures and densities found in collapsing stellar cores. Physicists have built models, equations of state, but the models have uncertainties. Different models give different predictions for the maximum mass of a neutron star. Some models say 2 solar masses, others say 2.5. The observations are starting to narrow the range. LIGO and Virgo have detected neutron stars with masses just over 2 solar masses. That tells us neutron degeneracy pressure can support at least that much, but the upper limit is still uncertain. And the transition between neutron star and black hole, the exact moment when degeneracy pressure fails and the core collapses into a singularity, that transition is one of the biggest unsolved problems in astrophysics. And then there is the singularity itself. The point at the center of the black hole, where general relativity says the density becomes infinite and space-time curvature becomes infinite, and the laws of physics break down. Most physicists do not believe the singularity is real, not in the sense of an actual point of infinite density. More likely, quantum mechanics takes over at some scale, the Planck scale, 10 to the minus 35 meters. At that scale, space-time itself becomes grainy. Quantum fluctuations dominate, and the singularity, instead of being a point, becomes something else, maybe a region of extremely high but finite density, maybe a quantum foam, maybe something we do not have words for yet. But we cannot test any of this. We cannot observe inside a black hole. The event horizon is an information barrier. Everything inside is hidden from view. And that drives physicists crazy, because the singularity is where the most extreme physics in the universe happens, and we cannot see it. We can only infer, only model, only guess. A full theory of quantum gravity, one that unifies general relativity and quantum mechanics, would probably resolve the singularity, smooth it out into something finite. But we do not have that theory yet, not even close. String theory is a candidate. Loop quantum gravity is another, but neither one is complete. Neither one makes testable predictions that we can verify with experiments. The singularity remains a mystery, a signpost pointing toward physics we do not understand. But the universe does not care that we do not understand it. It keeps running. Stars keep collapsing. Black holes keep forming. Jets keep erupting. Hypernovae keep exploding. And the heavy elements keep scattering into space, seeding the next generation of stars and planets. The process is indifferent to our ignorance. It has been running for 13 billion years. It will keep running long after humanity is gone, long after the sun has burned out, long after the Earth is a cold, dead rock orbiting a white dwarf. The universe will still be here, still forging elements in the cores of massive stars, still scattering them in explosions, still building new worlds from the ashes of old ones. The cycle is eternal, as long as there is matter, as long as there is gravity, as long as there are stars. And that is the deepest lesson of the hypernova. The universe is not hostile, it is not friendly, it is indifferent. But in its indifference, it creates, it builds, it takes matter and energy and time and turns them into stars and planets and, eventually, life. The violence is not a flaw, it is not something to be overcome, it is the mechanism, it is how the universe works. You cannot have creation without destruction. You cannot have new stars without old stars dying. You cannot have heavy elements without supernovae and hypernovae. You cannot have planets without the debris from exploded stars. You cannot have life without the atoms forged in the cores of massive stars and scattered in their deaths. The violence and the creation are inseparable. They are the same process. And you, sitting here, made of atoms forged in dying stars billions of years ago, scattered across the galaxy in explosions that outshone entire galaxies, slowly drifting through space until they condensed into a molecular cloud that collapsed into the sun and the planets and eventually became you. You are proof that the process works. You are the universe looking at itself. Atoms arranged in such a way that they can contemplate their own origin. And the origin is violent, it is chaotic, it is beautiful, and it is still happening right now. Somewhere in the universe, a massive star is collapsing, a black hole is forming, jets are erupting. A gamma-ray burst is lighting up the sky. And the atoms forged in that explosion will drift through space for billions of years until they end up in a new star, a new planet, a new world, maybe even a new form of life. The cycle continues, the violence continues, the creation continues. And the universe, indifferent and relentless, keeps building. So here we are, standing on a small planet orbiting an unremarkable star in the outer arm of a spiral galaxy that contains hundreds of billions of others, looking up at the night sky with instruments sensitive enough to catch light that left its source when the universe was young. And what we see when we look far enough, when we catch the right flash at the right moment, is violence, not random, not meaningless, but violence that builds. A 40 solar mass star collapses in less than a second. A black hole is born. Jets erupt at 99% the speed of light. The star explodes with more energy than 100 billion suns. And in that explosion, in those few seconds of unimaginable chaos, the universe writes the periodic table: carbon, oxygen, iron, zinc, gold, uranium. Every element heavier than helium, forged in fire and scattered across light years of space, drifting, cooling, mixing with clouds of gas that will one day collapse to form new stars, new planets, new worlds. You are made of that debris. The calcium in your bones came from a supernova. The iron in your blood came from a hypernova. The atoms in your body are older than the Earth, older than the sun. They were built inside stars that died before our solar system existed. And when those stars exploded, when they tore themselves apart in the most violent deaths the cosmos can produce, they did not just destroy. They created. They gave the universe the raw materials it needed to build you. The jets have long since faded. The gamma-ray bursts are over. The black holes remain, spinning in the dark, invisible. But their legacy is everywhere, in every star, every planet, every living thing. The most violent death in the universe is